So in 1980s, computer vision, people work on shape from motion, shape from stereo, start work on 3D object reconstruction. Yes. Slide done more. So the Google Slides also is some little problem here. So
Okay.
okay, now it's come. Okay, yeah, thanks.
Wow.
So we talk about LiDAR. LiDAR has been used for 3D building reconstruction in mid-90s. Actually, in photogrammetry field, people start to use LiDAR for mapping, especially for building reconstruction. And since then, we have images and LiDARs for building reconstruction. During the 20s and 2010, many methods are proposed. Image or LiDAR-based building reconstruction methods. Of course, is traditional. We know after 2012, we're entering deep learning age, right? So we focus on the building reconstruction, but if you look at the past decades, there are not many deep learning methods for 3D building reconstruction because we lack of such data set. So, Google Slides also okay. So in last year, actually we released the first LiDAR point clouds to wireframe building data set. So we hope with this data set we will have more research on the LiDAR point clouds based 3D building reconstruction, and also we host a challenge. This challenge will use this data set and in 2024. And the whole is Hover company, they release this image to wireframe building data set. It's from image to 3D building wireframe. There are not many such data sets. I think it's very few. So we hope with these two data sets we can promote urban modeling research in in this direction. And we just keep traditional building reconstruction and just talk about a little bit on LiDAR point cloud based 3D building reconstruction. You see, due to the lack of the building data set, people just, graphic people working on small objects. So this one paper in 2020, but this method is also suitable for building reconstruction. That's why we listed here. And you can see here in 2022, there's a deep learning method, but it's hybrid. They are not end-to-end method because we don't have data sets, right? So they just hybrid combine traditional methods with deep learning based method together for building reconstruction. And so this is the first end-to-end building reconstruction method, but based on the synthetic data. So that's why, so in 2023, we released this building 3D data set, which is real urban scale, the LiDAR point cloud based data set. And we have the LiDAR point cloud, have a mesh model, have a building wireframe model. And in this year, we already we published one paper based on this data set. Is for building reconstruction, and also this method serve as a baseline for the challenge, building 3D challenge in this workshop. Okay, so now I believe talk about this workshop content. We have 6 keynote speakers, 2 challenges, and 4 winner talks. We have the 7 accepted workshop papers and the paper spotlight. Lastly, we have this interactive panel. So this is our 6 amazing keynote speaker. I think they are from photogrammetry, from computer vision, from computer graphics. I think Eero and Conrad they working on the civil and architecture and motion vision, right? And Conrad is doing the photogrammetry and computer vision stuff. And Richard Zhang is from computer graphics. And Yasu, Lova, Thomas are very well-known vision research. I think everybody knows, right? So so this our challenges, okay? Building 3D challenges. Input is a 3D LiDAR point clouds, and the output is building wireframe. And second challenge is SQL 3DR challenge. It's given the image, so we run cone map or structure from motion. We get point clouds. The output is building wireframe. So we thank the sponsors. I think whole world sponsors $25,000 for this challenge. and the Pop Smart sponsored $10,000 for building 3D challenge. So without further ado, I think I will let Jack.
Please, yeah. So just introducing Iro Armeni. She is at Stanford, and she'll be giving a talk building a global resource cassandre.
Can unmute.
Yes. Yes. Can you hear me? Okay. Good. Okay, we solved all the technical difficulties. Good morning, everyone. Today I will talk about building a global resource cadastre. For those that don't know, cadastre signifies database, data management, etc. And essentially, I will be focusing on how can we leverage computer vision in order to advance circularity, climate mitigation, and urban sustainability in methods that can actually work today on a global scale. That's the main purpose. Now, between the complex ecosystems that Earth has, we have the built environment that is comprised by cities, by infrastructure, and by buildings. And these buildings in which we live and work and play, they are essentially a testament to human creativity and of architectural and engineering achievements, but at the same time, they have a very negative impact on our environment based on the aspects such as resource depletion, waste generation, greenhouse gas emissions, and climate change. Take this example of the skyscraper that requires a huge amount of material, particularly glass and metal, in order to be built. Or this concrete bridge that has a high embodied carbon, which means that for the very first product that gets created for this bridge, cement and steel, we have a huge amount of greenhouse gas emissions all the way until the end of the construction of the bridge, which accumulates, having hence a very high embodied carbon. Thinking that by 2050, there is a projection that the global population will increase from 8 billion to about 10 billion people, which means we have to accommodate in 25 years another 2 billion people on Earth. And that means, if I put it into perspective, that we have in the next 25 years be building 15 houses per minute in order to accommodate this urbanization growth and population growth. However, we have to consider this profound challenge that we have right now. How can we be able to support these housing demands while at the same time not having a negative impact on the environment? Essentially, is it possible to realize a future where our cities are symbols of sustainability rather than of excess, of waste, of greenhouses, etc.? Global data from the World Bank is pointing out a more planetary overview of the environmental impact and of the industrial trends that we are having today. Over here, you see right now the CO2 emissions per capita, which are demonstrated on the y-axis per year, essentially on the x-axis. And you are looking into 6 countries from 6 different continents that are 3 developed, the United States, Switzerland, and Australia, and 3 are the development, Brazil, India, and the region of South Africa. You can see over here as well a more planetary overview where the whiter is the lower impact of CO2 emissions, and the greener, the darker the green, the more high the emissions that we have. And you see this trend of more developing or developed countries to have higher emissions. What is particularly over here that I want for you to notice in this graph is that all the developed countries, the ones that have these little dots, essentially have high CO2 emissions. And if that is a historical trend that is now starting to diminish or becoming plateaued, and that is because we are shifting into more sustainable practices and efficient use of resources. Versus developing countries, such as Brazil and India, that are starting to become even more developing even more in their industrialization and industrial practices, which is a sign of economic growth because they are developing, right? However, that has a big impact, starts having a big impact in the environment. Looking now into the gross domestic product, we can see how developed nations have more fluctuating trends, which showcases that they are moving into a more service-oriented economy, where we are taking better look into how we are using the resources that we have, versus the developing countries that have a very abrupt increase into the GDP, which also points out to this increased industrialization. Finally, looking at the population growth, we can see that in the developing nations, we are having this increase in population, whereas in the developed countries, we are staying more or less the same, maybe slightly decreasing, which means that in the developing countries, we're going to need a lot of new housing, versus in the developed countries, we see that strategies are now focusing on renovation and reuse of buildings in order to accommodate a more dynamic population shift. So what do we get as conclusions from this data? First of all, that developed nations have historically and continuing having high per capita CO2 emissions from construction. And there is a need for more renovation and repair strategies in order to reduce those emissions. And then the population growth in the global south tells us that there is increased construction happening right now, which means that we need better strategies for sustainable construction and development. What we follow so far is a linear economy model, where we have resource extraction, production, distribution, consumption, and then waste of resources and products. And in this context of creating better strategies, we should focus on a more circular economy strategy, where we are reusing, recycling, and paying better attention on how we utilize our resources. And specifically, circular economy points out into eliminate waste through the redesign of materials and products, maintaining products and materials throughout the use of a certain, let's say the building, in a very, very good condition, as well as being able to add value and regenerate the natural environments by recycling or reusing materials. Now, how can we go into a circular economy strategy where we're going to try our best to make our buildings stand more as they are by repairing them or renovating them without adding too much of new construction in it? Or even if we do new construction, we can reuse existing materials to build a new building. How can we achieve that when we have millions of existing buildings on Earth for which we have no data? So the global problem is that we're actually having insufficient construction data. And by that, I mean for how these buildings have been constructed, the ones that are existing. We are, as construction industry, we are not documenting the materials that we are adding to these buildings. And imagine that on Earth, we also have very, very old buildings from centuries old, right? So we could never have been able to trace this information over time. So we have an access of this comprehensive database to allow us to catalog these construction types and materials that existing buildings have or new buildings are having. So any database that we have in the global north, in the more developed nations, it is lacking of information. And anything in respect to global south is actually non-existent. The attempt to get this data right now for existing buildings and why we have lack of this information is because it's done in a manual auditing method, which means that people are going to go on site, are going to use very specific measurements and sometimes invasive techniques in order to understand what is the material and the composition of a certain building. That means that there is high cost, extensive time required and labor in order to get this information per building. Also, we have diverse construction practices, which doesn't allow us to create this very easily and make more generalized assumptions. And finally, we have an urban development that is dynamically shifting and changing, which means that we need to have up-to-date information. We cannot wait 2 or 3 years in order to get this information for a certain region that has been renovated. In order to better understand what is happening in that particular practice, we talked to many stakeholders that perform these audits in order to understand what's going on. And we asked them many different things, among which is, how costly is this to do? When we're talking about on-site inspections that actually you have to go on site to acquire all this data, essentially to the building, we're talking about $300 to $1,500 per property. And if you're going to do a desktop inspection from some data that you have digitally acquired, if this data is available, we're talking about a smaller amount. It's about 60 to 70 per property. However, this is not really available. It is very time consuming, and you need 3 to 4 hours per property, plus any time you need to travel to the building. And most of the times, multiple site visits are required in order to acquire the full information. And finally, with respect to labor and personnel, you require at least 3 to 4 people on site to acquire the data, 1 to 2 people in order to process this data, and at least 1 person in order to do sanity checks to make sure that actually everything is correct. Now, looking into material intensity studies, this has been researched in the past as well. And what is material intensity is essentially a ratio that relates the domestic material consumption to economic growth. And ideally, we want in a more sustainable world to, even though we have increased gross domestic product, essentially increased economic growth, to not really increase the domestic material consumption that we are doing. So keeping these two kind of non-correlated with each other. Now, related work in this field of material intensity studies, understanding what are the materials we have and how much they are changing over time, have been done. However, they are focusing on specific material fractions, such as minerals and metals, and they're not really localizing this material on the level that we would like, that is on a building level. Some of the studies are localizing with the use of information system. However, they are able to localize some parts of the building stock or some building types. However, there is no accurate material composition about these buildings. Other works are looking into on-site investigations using digital techniques such as laser scanning and other more invasive approaches. However, there's an issue of scalability because you cannot do that for the entire world. So how can we go today about creating a global resource cadastre? And the goal of the way we wanted to approach the problem is to make a method today that can be applied already by practitioners out there on a global scale, since this is such a pressing environmental and sustainable matter. And we want to create this method to provide information to stakeholders that is vital in allocating resources, in balancing supply with demand, and conducting economic analysis, all about urban development and making decisions in the future of how to distribute materials in a circular economy setting. And we thought, what is the fastest way to get this information right now? Well, we're going to use computer vision. Obviously, that's why we are here in this conference. And in addition to that, how can we find databases that are largely available to most governments or local governments or organizations? And that would be available Street View imagery. And of course, you can tell me that with Street View imagery, we cannot really get all the material composition, but we do believe that this method we are using can scale up to the interiors and address this kind of material composition as well. So for now, we are staying on the outside of the buildings. And we want to get an understanding of, on an urban scale or even global scale, what are the facade materials that we are using? That is a first step towards the circular economy strategy. So we're gonna retrieve street view imagery. We're gonna start understanding materials on the entire building, and then we're gonna go into the different facade elements and understand the material composition there. And once we have that, we can do urban analysis. How do we retrieve the data? I mean, it's obvious we get definitely street view imagery, but also we get any public related government data with respect to information about where buildings are located, potential use, etc. And in order to be able to specifically find the best street view imagery for a specific building, we do the following. So with the blue dots, you see the different buildings that are related to a map, and with the red, you see the different camera locations. So how can we choose the best one for that facade? We first of all decide to use any camera location that it is around 30 meters from that specific building. And then we look into the heading and pitch of the camera in order to make sure that the building is mostly visible from that particular location. Of course, we don't yet have a very good understanding of where the building is in the image and which one is which. So there is a chance that we might get a few more buildings inside the image, depending on the heading and the pitch and the size of the building. But overall, this has been working very well. And so from specifically this building and these 3 potential camera locations, this is the one that fits the bill. And so we end up with many camera locations per cities. And here you can see all the blue and the red dots that we are accumulating over time. In order to perform our analysis, we've now started, and hopefully we're going to be able to do the entire globe, but for now, we started with 6 cities from 6 different continents. We excluded Antarctica for obvious reasons. And so we have San Francisco from North America, we have Rio de Janeiro from South America, we have Cape Town from Africa, Zurich from Europe, Mumbai from India and Asia, and Melbourne from Australia. Now, how do we do the building level understanding, get some first information from the building? And so we have these images. And the first thing we need to do is we need to identify where the building is in order to facilitate the understanding of these materials in an automatic way. And so we use foundational models. In this particular case, we use Grounding Dino in order to specify where is the building in the image. And so we get a very nicely segmented mask that in the majority of the cases gives extremely high accuracy in defining this facade mask. And as we were doing that, our first approach was to consider a more supervised learning approach, where we would have to create and curate our own data set, train algorithms, and see how they would perform. But of course, since no data set exists, it would be a very time-consuming process. But as every researcher these days does, we ask this question, well, how would a multimodal model do, such as GPT-4, if we gave it this specific image facade, and we tell it, tell me the building materials? I will, spoiler alert, it does extremely good. And more importantly, we started by asking open-ended questions. We found that open-ended questions did not work extremely well, particularly with respect to the analysis of the data, because it was extremely difficult to make correlations between different buildings. So we decided with prompt engineering, as everyone does for foundation models, in order to make our analysis easier, to start making more structured asks and questions and queries to this model. So we asked it about the building style, with information about the main architectural style, the substyle, and defining features, because the building style and the year that a building was constructed, which can get from public government data, are very high indicators of the material that this particular building will have. The window types, the different facade components, and the building materials. In addition, we wanted to see if these multimodal models can give us more information about making decisions with respect to our urban landscape. And so for each of the cities, we asked it a different question. We asked it, what is the condition of that particular building and its heritage value in order to perform renovations in Zurich? Is it seismically okay, or should it be retrofitted? Are there any details of the facade that could point out that we need to seismically retrofit it when we are talking about such a seismically prone area such as San Francisco? What about energy efficiency retrofitting in Melbourne, which is a very big trend right now? About Mumbai and its challenges with urban density and building conditions. In Cape Town, with respect to temporary structures, which is a very big trend right now, they are renovating big parts of it. And in Rio de Janeiro, what can we do with respect to flood-resistant construction? Once we get this information, we kind of got a lot of high-level information about the building, and now it's time to go into more detail in understanding the materials of each of the facade elements. Guess what we used? Multimodal models. And so we are able to first get a facade segmentation using segment anything and a set of marks we're going to use afterwards as an input to GPT-4 in order to get understanding of the facade component and its specific materials. This is an example. This is a facade and the different segmentations that we get from SAM with a set of marks that we input to the GPT, and it gives us the following answer. The purple outline encloses what appears to be a window, specifically highlighting the lower portion, which includes the window sill. So we get a lot of information. This is about what is that facade component, and of course it tells us about the materials as well. Now, I have to point out that this is an ongoing work, so I'm not going to be able to show you all the final analysis and results. I'm going to show you what we have right now. So right now we have processed, and we're in the process of processing about 2,000 images per cities, and we hope to scale that more and more as we go forward. But let me tell you of a few descriptions that we got out of GPT, particularly for the building level understanding. Now, who can tell me out of the 6 cities, Zurich, San Francisco, Melbourne, Rio de Janeiro, Mumbai, or Cape Town, where this building is from? Let's see how much you're in your architecture. Who says Zurich? I see a few hands. Who says Mumbai? Really? Have you ever been to India? I'm kidding. Yeah, I'm joking. Who says Cape Town? Rio de Janeiro? What was the other one? I already forgot. San Francisco. Okay. Well, I see that you're very divided. This is actually from Zurich. So yes, good job to those. So let's see a little bit about what it gave us information about this specific building. Main architectural style, contemporary modern. Defining features, simple geometric forms, lack of ornamentation, and functional design. Now, this is more as a reasoning on why it shows this specific architectural style, because we found that if we understand the reasoning, we can actually understand if this is a correct or not answer that is giving. Sometimes, and particularly because a lot of the times it's even hard for architects that are trained, specialized, have a degree, have a license, like me, to understand what exactly it could be that style. But this makes it super easy, and I don't even have to think. I say, this is exactly correct. This is exactly the architectural style that it is. With respect to windows, it tells us the material, and it also gives us a certain reasoning about the choices it made, as well as for the facade components. It even is able to understand that there is a ground level glass entrance, even if it's partially visible. And then there are material highlights that tells us about the bottom and the top of the building, that it has 2 different materials. And it also says that there are unique features, such as the contrastive use of material to distinguish the base from the upper floor. So honestly, it does better than what I would suspect any human person to actually be able to do, spending like less than a minute on this image to provide this information with less cost than a human would do. I said that we also ask a few more specific questions for each region. So for Zurich, we understand the heritage value, and it tells us because it's very contemporary architectural and it has minimal heritage value based on these visible features. So it shouldn't necessarily be the first thing we're going to save and retrofit and repair as we go forward. And it thinks that the heritage score is low because of these specific features. And then it also tells us again about the different building materials per what we asked it to tell us. Now, this is another building. Which city? Zurich? San Francisco? Cape Town? Mumbai? Melbourne? Okay, don't see everyone participating. But this is Zurich again. If you see, there is a slight tendency towards there. And you will see why based on my collaborators afterwards. So the building style here, the architectural style is Renaissance Revival. By the way, this is what it looks like. The material says stone or stucco surrounds, glass panes, framed possibly with painted or wood metal. There are doors and entrances with elaborate stone surrounds. And I want to focus on the heritage value, which says that it has historical significance, and it even can tell us more or less at which period of time this could have been constructed. And it gives a very high heritage score to this particular building because of the local historical importance and the architectural features. So it's actually able to understand about the context that it is in Zurich and can have a high local importance, because we do tell it this is in Zurich. And then it tells us about the building materials, and it's able to also make some assumptions and tell us that it makes assumptions that in the roof, based on similar buildings with similar roof types, we think that it must be slate or some kind of similar kind of material on top. I'm not going to go into more of these examples very quickly. I want to showcase about San Francisco, how it tells us that this is it really needs to be seismically retrofitted to be more stable. And the reasoning is actually spot on. The building has a visible garage with a door that may indicate a large opening at the ground floor, a characteristic soft story condition. This is a thing that we have in civil engineering. And the presence of a garage and potentially other large openings with minimal wall support along the ground story indicates a potential risk in case of an earthquake. What does that mean? Because you end up having a big mass on little columns, it is extremely easy to just break and fall, as like very, very abstractly and non-detailed, non-professional way of describing it. Okay, in Rio de Janeiro, last example with respect to this, we have a condition score that is low for this building because it's able to understand that there is discoloration on the walls, possible water stains, and peeling paint. I'm personally very amazed by the results that this can give us based on, I show you the numbers of how much it costs to get it manually audited. Okay. Now, I'm going to show you a little bit of urban analysis for Zurich to start making some understanding of how it looks like. So this is the center of Zurich. Here's the train station. So for those that don't know about Zurich, this is more an older part of Zurich here as well. So we see a lot of older buildings here as we start making a little bit more modern. And what, am I even showing with my mouse? No, I'm not. Okay. Here is the train station. Here are more older parts. Here we have a little bit more newer parts, but in general, it's a lot because it's the old part of Zurich. We are talking about older buildings. And you can see the different architectural styles with different colors. You can see there is a mix of architectural styles in the middle of Zurich from different from different chronologies. And you can see that a color that really pops out is the neoclassical with the yellow, that you can see mainly into this old part of Zurich, which makes sense because that is what you can actually really find in these particular areas. Now, the building condition, as you see, in the old part of Zurich, they have done a very good job in being able to have good condition on their buildings, which means they are not in immediate need of repair. Unfortunately, the coloring is a little bit opposite. So good is red, and poor is black, which is not visible, students, and fair is green. That's that. And all the blues are things that cannot be determined by GPT. Okay, so you see that in general, Zurich doing very well in keeping things in a very good standard. And here, I want to show you about the heritage score of the buildings that we have so far processed. And I also give a few images to show you what is of the architectural style, what it is, because you might not be familiar with them. The architectural style with the most importance for heritage, and that should be better preserved and repaired, it is the neoclassical architectures, which is these red columns here. So as you see, the rest almost not have any kind of high heritage values, the rest of the architectural styles. What is interesting also to understand here is the decorated modernist and the functional modernist. So modernist would be more like a very modern building, not necessarily high-tech like these skyscrapers, but less ornamented than a neoclassical building. And you see that the one that is decorated has medium heritage score, and of course low, but mainly medium, versus the functional modernist, which is more simple, not ornate, which is mainly low heritage score. And I have to say that I see a little bit of a trend in GPT-4 to consider that the ones with the more decorations are the ones that should have the highest heritage value. That is not necessarily always true, because we have a lot of great buildings in the modernist era or postmodern era that should still be preserved for later generations. However, as of now, this is what GPT-4 gives. All this we're trying to also verify with humans. However, things are extremely simpler to verify if you already have this information, and then a person needs to say yes, no, and if no, change the question. So we hope that it's going to be very fast and cost effective to verify all this information that we're doing. I want to start concluding by mentioning that, of course, there are certain limitations with respect to this method. Since we haven't concluded the processing and the entire analysis, I will point out the ones that are right now obvious to us. First of all, we do not have any temporal relevance in our data right now. What do I mean by that is that we have downloaded Street View imagery from the latest data point collection. From the sources that we try to access, there is no chronological information in order for us to acquire. But if we do that over time and we keep up this work running in the background, we hope to be able to accumulate all this information over time. In addition, image resolution is an issue. A lot of times image resolution in this Street View imagery cannot give us very good crisp building masks and segments at the end. You know, imagine these little windows that we get in order to give it in GPT-4. It's particularly small, and we all know how for materials we really need good texture, which means higher resolution. So, you know, if anybody's working on Street View imagery, please use better sensors in the future. Thank you. And finally, there's the issue of coverage inconsistencies because not everything is mapped. Of course, we are talking about urban environments, so we are for now focusing on that, which means we're gonna for now miss all the non-urban settings. But even in urban settings, there is a lot of issues with respect to roads that exist or not exist, especially in developing countries where the landscape changes so drastically, it would be hard to keep up. However, we do believe that this method has a potential for widespread application in sustainable urban developments. It is scalable, costs less. I don't have the numbers right now, but for the projections we have, it costs way less than actually doing the manual auditing. It gives extremely good information and highly accurate so far, and it's adaptable to different types of data, as well as different types of environments. So I could see very easily this being applied to indoor environments as well, in case you wanted to understand the indoor material and condition of a certain building. Now, if learning about buildings has been extremely interesting to you, we have tomorrow a workshop on computer vision in the built environment, where we have 6 amazing keynote speakers coming to talk to us. 3 of them are more applied, and 3 of them are more technical. So you can have, you know, this kind of diversity in the opinions that you will get. And if you generally like buildings, and you are also interested in the spatiotemporal aspect, my students are presenting their 2 works this Friday in 2 different poster sessions. So feel free to stop by and say hi. And with that, I want to thank my collaborators. And now you understand why we are more, you know, tailored towards Zurich examples at the beginning, because they're all from ETH Zurich. Okay, and with that, thank you so much, and I'm open to any questions.
I have a question, which is probably hard to answer. Yeah. So have you checked how well sorry, global thoughts styles are represented and detected by GPT-4? Because I recall, I think there would be paper on CPR saying that current VLM models are very kind of shifted to European and US recognized styles as well, and much worse for India and in other countries.
Do I need to repeat for Zoom?
No,
it connected? Good. This is a very good question. As I said, our analysis is underway. By the way, tell me this paper afterwards. I would love to stop by and see it. Our understanding so far is that it's doing very well. But again, our analysis is underway and our verification is underway. So we'll find out soon. Yes.
Yeah, I think it's very interesting ideas to use GPT-4 or let's say foundation model to infer the building material. But I wonder, because you only take the image, right, Street View image, but you can now reason the thickness, right, of the material. But that actually relevant to, let's say, carbon stuff at your first flights, right? Have you thought about how you can reason about how thick this material? I don't know if I.
Yeah. This is a very good question. And it is a little bit outside of the scope of this particular research. We are trying to also quantify as much as possible materials and so to have very precise kind of volume, at least information, very precise, relatively precise volume information. And so far our strategy would be based on the particular architectural style, the chronological construction of that particular building, and the material that it's supposed to have based on GPT-4 and our verification to make certain assumptions about the width. There is a possibility to do a more precise job as maybe a government that has access to all the building permits, as long as there are building permits for each of those buildings. So you can actually get information precise about the widths of all these components and even more precise measurements than what we can predict, let's say depth prediction, molecular depth prediction from those images. Yes. So essentially organizations will have even more information in their hands. Yeah.
You mentioned the problematic bias in the heritage score.
Mm-hmm.
How do we overcome that?
This is a great question. So this is so far a first understanding of the results. I need to see that a bit more, but I think that it is, there are very specific people with very specific expertise that also define what is supposed to be of heritage or not. So I'm sure that if you prompted GPT-4 in a more appropriate way that told them, this is the things that usually heritage buildings should have per chronology or per type or whatever that would be, I'm sure it would do a better job than what we have right now. It does become way more technical, but it is also true that the more decorated things are, the more old they are of years, because we tend as architects to simplify things, and newer buildings tend to be more abstract and simple in lines. Yeah, hope that answers.
Street with their images, with images of inside the place, and how they live, what they eat, how their toilets look like, things like that. So are you trying to embrace more of the cultural space and people and living areas into this format?
Let me think how to answer this. I'm not sure if you're talking about the residents and their culture. I'm wondering how much that affects the specific construction of the building. You know, if you're renting a place, you're not really changing its construction and its materials. However, I think it is important to understand more information about the building space in this particular sense. Of course, getting data from interiors and having more specific material composition for interiors is extremely useful, but for now, we are sticking to the outside. We're essentially trying to build a tool that is particularly suitable for urban developers to get fast, quick information to get into circularity. Thank you.
So final question. I was very interested at some point to find out that urban developments or urban like cities grow in fractal nature. I think that was a research somewhere.
Sir, can you repeat?
So cities apparently grow in a fractal manner. Is it still the case? Is this still the current model or not?
That I don't know. Yeah, I don't know what's my speculations.
Let's thank Eero one more time.
Thank you so much.
That speaker is Conrad. I can't please set up the computer, then I can have a brief introduction for you. And yeah. It's not yet projecting. It's in projection mode. This again go here. Yeah. It's super slow. That's going on. And now I need to get this to share this one. Yeah. Okay. Thank you very much for the invitation, for having me. Can everybody hear me on Zoom and in the room? Zoom is also working?
No.
I
Share Zoom share. Because I think on the room is that it's not shared.
where's the Zoom?
I think you need to enter the full screen mode.
I'm not quite sure what I have to do now.
Let's find the Zoom interface that you have.
Wait, I can end this.
This mic.
So the sound is on.
Mute that and bring this here. And then share. I can turn it on. It's not okay. Which one you have?
Yeah, but now it's not. I mean, I first have to get this into projection mode, right? So. No, it's not. I don't know how this is working.
These guys as well. It's connected. It's just that when it's on full screen mode, it doesn't show up down the Zoom.
Okay. So I go to share screen.
Is that the one that you tried to present?
So here it is showing up, I think, but I'm not sure.
Someone, you have to move your mouse maybe over there to click on resume share.
I'm not able to get my mouse on, but it's a second screen.
Oh, there.
So what do I do?
There, up there, resume share. Yeah, click it.
It's not working.
Click it. Screen share on the phone. Maybe click stop share.
Yeah, and start again. And now should I share again?
Share screen, yeah.
Yeah, I have to find my mouse pointer again.
like desktop one.
This one, this one too, is that
Yes. Oh, yeah, there was sure sound. Yeah, but-
It's working. Yeah.
Cool.
Okay, so now I don't see it, but I think that shouldn't matter. I'll go here. So can everybody now hear and see? Good. Okay, thank you. So the title of my talk is Urban Modeling in the Deep Learning Age. And the idea was here, what do I talk about? I mean, there are hundreds of works, and I thought I'd give it a little bit of a historical perspective. So I started before the deep learning revolution and thought about what did urban modeling look like at the time. Looked back a bit at some works that I remembered and liked. Coincidentally, actually, they are, which is probably a good thing, by some of the organizers of this workshop. So at least Florent, Clément, Ilke are among the organizers of this workshop, although they're not here. So apparently they have been doing good urban modeling for a long time, which is not surprising. These systems worked fairly well. You see what they could do. They could go large scale. They could get pretty nice building models. They were just a little bit hard to tune up and to make work. I forgot that I should maybe say that this talk is specifically about large scale, so airborne or satellite-based modeling, not ground-based, taking the sort of photogrammetry and remote sensing perspective here. And these things were really great, as you see from the models. But they were, of course, complex systems, which means that there were many intermediate things that you had to set to just the right value to make them work. And then I thought, what happened in the past? Where did deep learning contribute? And I'm going to show you some examples from our work. So the idea is, okay, now, as everybody knows, the deep learning wave sort of washed over everything, not only over computer vision and all other sorts of perception, but of course also including city modeling and remote sensing. And this came in several waves. And of course, when the stuff came around, we tried to play with it and use it for our purposes. And I'm going to show some examples. So I'll start with the first wave. And the first waves were obviously CNNs. So that was the start of the revolution, convolutional networks. And for our purposes, where we want structured output, this in the end means image-to-image translation. So encoder, decoder that somehow take an image and they output something else that is also so spatially explicit. And we were thinking, this is now about satellite-based sensing. So we're talking about sensors that are really far away. The best satellites that you can get, unless you are a member of the US military intelligence community or the Chinese one. So if you're a civilian, the best images you can get have about 30 centimeters ground sampling distance, so pixel footprint on the ground, 30 to 50, depending on the viewing angle. If they look to the side, of course, you get some distortion. And that means that you don't see things in great detail, but you get great coverage. And so there was for a while already a drive to use those satellite images to do modeling of urban spaces, also of other spaces, but urban in particular. So we want a surface model, we want a 3D model that represents the urban space and that we make directly from those satellite images, since the satellite moves and has different perspective. This, of course, calls for stereo or multi-view stereo reconstruction. And that's how it was done. So you take multiple images from different viewpoints. Often they are also slightly temporally offset, but that's a minor detail in this context. And then you run a conventional stereo pipeline. The pose estimations, or the pose is a little bit different in terms of camera models, but by and large, it is stereo triangulation. So you do dense matching, you triangulate the rays, and then you get a point cloud, and that looks about like this here. A point cloud is, of course, very noisy if you take it from that distance and with often suboptimal stereo angles. And then you do your best to turn this into a surface model by some robust filtering and trickery. And you get the surface model there on the right. This is actually not exaggerating to make things look bad. This is a real satellite-based piece of stereo model done with a reasonably state-of-the-art conventional system that is actually also, that was in part co-developed in my lab, but it has been built into commercial applications by now. So this is what it looks like. And that's not because the methods are bad, but that's just because the data is very, very ugly for high precision modeling. And the right side is the ideal thing. The right side is what you would like to have. This is ground truth, if you will, manually created CAD level city model of the city of Zurich here. And we asked ourselves, how can we bring those two worlds together? And so can we do something with learning, but we don't want to work from scratch because, of course, all the stereo geometry, all that knowledge needed to be used. And so we came up with this idea of you doing refinement instead. If you will, it's a sort of a residual learning strategy. You take a conventional one, you create the best you can, and then you try to fix its errors. So you do an additive correction at every location to make the model better. And that additive correction is all the complicated stuff that the geometric pipeline can't do, so you learn it. And you minimize a loss relative to, you do it supervised, so you take the city model and you train it, and then you hope it generalizes. And an important thing is you can, of course, just take the image, put a network on top and say, make this image better, make this height model, this surface model better. But that will be purely geometric filtering. There is no data there. There's no observation beyond just you have a surface, you make it a better surface, which is a bit naive if you start from images. So of course we said we include the images. The way we do this is we orthorectify them. So we basically texture map them into a vertical view, but based of course on the imperfect model that we have, because that's the only one that's at hand. It doesn't matter, luckily, because the errors that you get because of the height errors, because of the surface errors, are very systematic. They create systematic patterns. If you rectify against the wrong thing, then you get certain shifts that that have a pattern, so you can also use those to improve things. And of course, the images help you because they have sharp edges and so on, so they help this system to learn. And then you got this prior of what the surface should look like, which you have learned, and you apply it. This should be as generic as possible. So of course it should generalize across space and possibly also across different cities if possible. It will not generalize infinitely, of course, because it's still a learned system. So all the biases will remain in there. And importantly, it should also generalize across different viewing geometry. So just because the stereo pair has a slightly different baseline or a slightly different lighting, you don't want this to break down. So we have to solve this essentially brute force by augmenting the training data. So it's actually a very simple strategy. You run your good old stereo matcher, you create the surface, you're not happy with it. So then you take the surface, you take the rectified ortho images on top, and you give all this to a neural network, and you say, make a better surface model. So we hope you have a prior inside that knows what cities should look like. Remember, I'm talking about the first generation of deep learning, the CNN age. Here is an example of what we came up with. So the left side is the raw input from satellite, and the right side is then the refined one. And you have to watch the video a bit to get used to it and see the differences, but you do see it's not just the denoising, it actually has a very strong prior about architectural shapes, about plausible building layouts. So it did a good job. A side view, I have to admit, one part why it looks so good is also a data bias, a wanted data bias, which is that the target model used for training has no trees in it. So it learns to remove all the vegetation, which of course makes the height model look a lot cleaner too. But you do see that out of weird shaped blobs that happen due to the limited stereo resolution, it actually manages to make proper buildings, and we were quite happy with that. Yeah, this worked fairly well. You can also quantitatively show that it's good, so it actually decreases the errors by quite a bit. You can ask, do we need the images? The solution is yes. Of course, a learned filter is still better than just some very naive filtering, some median on the height or something. So it does work by itself. But if you add the images, things get a lot better. And this is mainly because it learns to see, to reproduce the sharp gradients, the nice edges and discontinuities that tend to be blurred out a bit by the stereo matcher. Adding a second image makes it a little bit better. That is a mild stereo effect. It's mostly just redundancy. You can now, of course, say, well, we have a system that works, but now we were rectifying against the bad DM. So why don't we repeat the process? And you can iterate that, but it converges very quickly. So it's not really worth going any further. Is it geographically overfitted? Well, everything is a bit overfitted, but not too bad. So we managed to train it on Zurich and run it on Berlin and vice versa. And it worked quite well. The urban styles are, of course, not the huge difference like between, say, an informal settlement somewhere in the global south in New York, but at least they are on a slightly different scale and in a different architectural style. You lose a little bit, but not too much, is sort of the bottom line. And then what was really important was to make this robust across viewpoints. So you don't want the thing to learn by heart that the stereo baseline between two images is always the same. The shadows are always the same. So we had to take the trouble to create different stereo pairs and show it a variety for the same locations so that it really learns to abstract that out. Then there's some, I don't want to go into detail here, but there are, of course, some engineering tricks, like you have to do a clever topographic normalization because otherwise cities that are in hilly terrain, that are on slopes, are treated very differently than flat ones. And if you train on one, it doesn't work on the other. So you have to do some sort of clever relative normalization of this. Also interesting, of course, in architecture, you have surface changes and the model, the ground truth, is not necessarily synchronized well with the imagery you have because these models are not updated so frequently. The good news is it works. So here's an example where they did a large construction project and changed an area. So that's the ground truth in inverted commas, because it's actually wrong. It's the old state. And these triangular buildings are the new version. And if you run the thing, it will actually recreate the triangular ones, except there is a thing. If you use them as training data, there is a memorization effect, right? There is a danger that it learns it by heart. So you cannot fix those areas which you use for training. You can also only fix the areas that you didn't use for training. Further typical learning biases, of course, this is the sole highest skyscraper in the city of Zurich. And if we exclude it from the training data, then it is actually shortened by the system, which is, of course, bad. Why is that? Because all other buildings are at least 40 meters lower or 30. And so you learn an upper bound. Of course, you're training your system on millions of examples and say the highest building ever should only be 70 meters. And then if you give it one that's more than 100, then it will correct it down and say this is too high. So usual learning limitations. We should probably have more training data from New York here. So that was the very first attempt to use deep networks for this reconstruction on our side. And then, of course, came the second network wave when people say, but surfaces, you don't treat them as pixels. You do something cleverer. You build implicit surface models and neural field type things. And so we try to upgrade to there. This, by the way, is work that also included Eero. It grew out of a student project that we did together at ETH. So instead of this explicit surface representation, we now want to fit a neural occupancy field. So essentially a neural network that gives you an implicit function that tells you, am I inside or am I below the surface or am I above the surface? So it's this sort of function, right? It's a typical implicit surface representation, and the parameterization is a neural network. So you give it a coordinate, you give it a location, and you ask it the question, am I below or above the surface? And if you have that function, then you can quite easily find out where the surface is by just sampling along some ray. So the overall approach, similar problem looks like this. You again have the images, you reconstruct a point cloud, but you now don't turn that point cloud directly into a surface model. You say that's our raw input, so we encode that. We do some clever neural feature extraction. We run this through an encoder. And then we also create the DSM. We need that only to orthorectify the images so that they are aligned. And we also encode those images. So we stick them through another encoding neural network that creates a second set of features. And from those features, in that feature space, you can now interpolate a location, and you can ask for that location and build this implicit surface model. And the implicit model is implicit, as the name says. So if you want to reconstruct a surface, you actually have to make it explicit. So you can do some marching cubes. In this case, when it's a terrain modeling, you can actually do something cleverer and directly sample, do some bisection search along the vertical, because you still know that there will be a 2.5D surface in the end. And this might seem like more complicated, but it does actually give you the advantage of added detail. So I hope you can see it, but this then really reconstructs dormers that are on the size of 1 or 2 pixels, so very small structures. So the implicit surface model can better use the same information to have even more fine-grained details. Of course, it's a relatively incremental improvement as usual. You know, it's this law of diminishing returns. If you have something that is already quite decent, that it's hard to make it better. But very consistently, we can get smaller details out by this formulation. Of course, the price to pay is also it's computationally more expensive. Again, the image guidance helps. So it's good to take the trouble and not only do a surface refinement, just stick a prior on your preliminary reconstruction, but also look back at the data, because straight lines, contrast edges, shapes are actually clearer in the images. Plus, you also have the multi-view consistency. So the inconsistencies between your rectified images and the surface tell you where the mistakes are, which is another advantage. You see that I shouldn't walk away from the microphone, I believe, but you can see that these very fine details here. Maybe I can get my mouse pointer on there. You know, these little dormer structures and so on. It's actually quite amazing that you can get them out of satellite images. Also, this one, we tried to do geographic generalization. It actually works. We didn't test it as thoroughly. There was an issue with the quality of the models from the other city, but it does seem to actually generalize slightly better. So it has less of an overfitting to particular locations and styles, and seems to be a bit nicer in getting geometry out of those satellite images. Okay, and then of course, even that is old now by neural network standards. So let's come to more of the present, the third neural network wave. And I guess by now the universal model for everything is sort of a transformer. So everything is cast as sequential token prediction. And then we thought, where can this be used for our purposes? I will give a high level explanation here and not go into details. The reason is that Yuja, back there, who was the lead author of this work, will actually present a poster this afternoon about it. So I don't want to steal the thunder and just give you the principle so that it fits nicely into this sequence. So we try to do geometric modeling as a generative sequence prediction task. I have to switch gears a little bit here. We go away from the satellites and we go to airborne LiDAR. So these are point clouds acquired by laser scanning from images. And our goal is now to make structured models. So we really want polygon models, not just a raster, but we want the sort of CAD-like models consisting of polygonal surfaces. The way that users actually like them, you know, user-friendly, structured models. I wouldn't call them fully structured. They're not quite constructive solid geometry, but of course, semi-structured and low surface count, efficient rendering. So that's what the data looks like. If you simply segment it into individual buildings, you do see the geometry, but of course the point density is uneven, especially on the walls where you have these very grazing angles of the laser scanner. There are data gaps, there are occlusions. So the data is good, but it's not perfect. And we want to have a polygonal mesh more like the one on the right. That would be our ideal thing. So really low surface count, not unnecessarily cutting up big surfaces into small triangles. And that includes that you should give it the freedom to not only have triangles. It shouldn't be a triangle mesh. It should actually be a polygonal mesh, because there are some surfaces that are very easy to produce with a single polygon, but you have to cut them up into many triangles. And what's more, there's a technical subtlety here. If you cut up a polygon into multiple triangles, there are many ways of doing that, which creates ambiguity, which this will be sort of randomly difficult in every model, and that actually makes it harder to learn because the pattern is very messy if for the same shape you have 10 different decompositions. Okay, so how do we represent everything? We say everything is piecewise polygonal, so the model consists of a bunch of vertices, which are sort of the corners of the structures, and a bunch of faces, which are polygons that are made by linking up those vertices. So you have vertex coordinates, and then you have sort of an index that tells you which vertices in what order form one polygon. And we do this in 2 steps. For those who know it, this is sort of very close to the polygen model from DeepMind. So you first predict the vertices based just on data, conditioned on data. And once you have them, you do a conditional prediction. You say the vertices are now the truth, and I look for the faces given those vertices. So it's a 2-step model. And now the only question is left, how do you turn it into a sequence and tokenize it? So that's the usual exercise when you work with transformers. So what do we do for the vertices? We order them lexicographically by the coordinates. We start with the vertical, so it's Z first, then Y, then X. So first the lowest Z. If the Z2 have the same lowest Z, then which one has the lower Y, and so on. So there's a unique lexicographic ordering, and you flatten that into a long sequence. And since you don't know how many vertices there are, you have to put a stopping token at the end, just like in a language model. So now we have turned the list of all vertices that we need into a sequence. And then we have to do the same with the faces. And there again, lexicographically by the index. So you cyclically permute until the smallest index is the first in a face. And then you say the one with the smallest index starts. And if 2 have the same index, then the next lowest index counts, and so on. And you flatten those into a sequence as well. Now you need 2 types of stop tokens. One says we finish a phase, because a phase can have varying number of points. And one should say, is the end of the entire sequence. We're done. And then again, you have something that looks very much like a token sequence, so you can handle it with the transformer. The last thing is, of course, you want the vertex as well as the other prediction to be based on the data. So you need to encode the data, and that we do with the pretty standard sparse 3D CNN. So you take a convolutional encoder that voxelizes and discretizes the space, creates a sparse voxel grid of convolutional features, and that one is the conditioning that goes in, and then you can attend to it so that you follow the geometry. So you have one level that generates vertices. It says, given the sequence so far, what's the likelihood for each on a discrete set of, I think, 256 possible Z values, what's the next one? And once I've done that, what's the likelihood of the next Y value, and so on? You can get ambiguities there. That's wanted, right? It's a generative model. And you keep sampling until you stop. And then next you go into the second transformer and say, given these vertex encodings, what is a good way to build a face? So build a face, and when you think you're done, say stop and build the next phase until you think you're completely done. So that's really how it works. Transformer layers that, well, for the vertices, it's easy, because for the vertices, you discretize the coordinates to a fixed set, right, to 256 values. And then it's clear that for each of them, you can make a prediction. So you do a categorical distribution over the 256 values, and you can pick some that have high probability with nucleus sampling. It's a bit more tricky for the faces, because the number of entities is unknown, right? You don't know in advance how many vertices there will be. And there's a trick due to Oriol-Viñals, which is called a pointer network. So essentially, you keep the embedding vector, and then you predict an embedding vector, and you do an in product and look which one is most similar. So the probabilities and the in product between your output and all possible answers. And that means that the set of all possible answers can have varying length, because you can compute that in product as often as you need to. There is one thing, those models are really cool, but as those who have worked with generative models will probably agree, they are not very good at hard constraints. They tend to sometimes still do stuff that is ludicrous. And so you have to check for that manually. You let the thing sample, but you actually babysit it and have some hard rules. And whenever something violates those rules, you chuck away that sample and backtrack and restart. So there are obvious syntactic rules, right? So the stop token has to come after an X because otherwise you have an incomplete coordinate. The coordinates shouldn't decrease because that's how we have defined them, and so on. For the faces, there is this thing that they should also be in increasing order. The first index has to be at least as large as the previous one because that's how we have defined the ordering. An index cannot be used twice in a face. All these very obvious syntactic things you have to check because the transformer will learn to not do that very often, but sometimes it will actually create such syntactically invalid objects. And then what's more is it's not only syntax, there are also geometric configurations that we know are implausible, but that apparently doesn't 100% extract from the data that they're impossible. So there's things like if there's a vertex missing, if, for example, if you have verticals, holes in the vertical walls, so there is a wall, but there's a triangle missing and so on, or the ground plane is actually not covered, right? You look at the footprint and then not all of it has even got polygons on it, then you know something didn't quite work. And then you have to tell the thing, try again, do better. This is not very elegant. It's a bit of a hack, but unfortunately, we found that it's necessary. Okay, so here is the City of Zurich data set where again, we have a nice bit of data. So we take a lot of it to train and then we test on the rest. I'll just visualize the process. And as I said, if you want to know more details about all of this, please in the afternoon, go talk to Yugia. She'll be happy to explain and she knows the details much better than me. So here you have the transformer in action, creating vertices one after the other. And when it thinks it is done, then it starts doing faces. Here are some more, just to see that it's not too picky about the type of building. It is relatively flexible. This will probably go out of sync because they don't have the same number of faces either. Okay, so some eye candy, some pretty examples if you do this for a larger area. We also went to other cities, like we did, what did we do with Zurich, Tallinn, and Berlin, I think again. And you can see that it's reasonably good. What it actually can do, for example, besides the small details, it can do realistic building roofs, which means it can do the overhangs. That's because we're no longer having this, I mean, you lose water tightness. You have to afterwards do water tightness post-processing, but you can actually have a wall and then you can have a second polygon that overhangs it, which gives you realistic roof shapes, which is something that has been notoriously annoying in city modeling, that you always get the roofs and then you just extrude them down and you get these boxish things. And of course, as I said, the price to pay is you're not watertight. You're only approximately watertight and you have to do some post-processing because every polygon is by itself. But still, you see that it's actually quite nice what this thing can do. Yeah, more cities. I guess I show you some other examples. This is Berlin with bigger buildings. Here we're a bit, we have to say that here we cheated slightly because here we had to use the cadastre to cut it into individual buildings because they are not detached from each other. Okay, so that was the overall story. And what do I deduce from this sort of historical view of our own work? And of course, of a lot of other work that goes down the same lines. We're not the only ones to have worked on this. My take-home message is that the great strength of deep networks or AI or whatever you like to call it for urban modeling is not so much feature extraction, feature learning, but what it is really good at is representing implicitly the a priori knowledge, the sort of prior probabilities over the shape and layout of the objects. So that was our grief before. We had to do a model-based approach or a rule-based thing where we would write out all the possibilities of how plausible is it that two building walls are parallel or non-parallel and that some little dormer is sticking out here and not there. and that a building has an overhanging roof or not, and that there are the small structures are aligned or not, and that the neighboring buildings are aligned or not, and that a building is triangular and not rectangular. And for all this, you sort of had to know, is this a defect? Is this a problem due to bad data, or is this really the case? So what this prior about shape and layout is very hard to hand code. And there, apparently, the networks are, again, very good if you just show them enough data. Of course, it's true that also the low-level features are a bit better. You know, we can describe the local differential geometry of a bunch of points slightly better if we learn it than if we just do PCA. But I don't think that that is actually the big difference. The big difference is this prior learning. It seems to get a broader, better applicable set of say, rules or regularities. But also there is this caveat that the hand-coded knowledge, to some degree, at least the most obvious plausibility checks, should actually, at this point, in my view, not be left to a network. Perhaps that's a matter of data, and if you train it on the entire world, you're done. I cannot make a statement about that because I don't have the resources to do that. But what I have seen pretty strong is that these models, as amazing as they are, somehow are not good at recognizing and respecting hard constraints or completely ludicrous cases. They, most of the time, they give you something useful, but sometimes they give you something useful with an important phase missing, or they give you something that doesn't quite make sense because you cannot decode it cleanly. And for that, it actually makes sense to still have a few hand-coded rules to babysit them. I hope at some point this will go away, but that's my current wrap-up of those projects. Okay. With this, thank you to all the amazing team, especially Corinne and Yuja, who are really leading this, but also all the others that helped. As I said, also Iro was involved in this, so congrats to her. That's where it all started. And with this, I'm done and happy to take your questions.
I have a question regarding these constraints. So what you're talking about, is this like you just use like pure transformer based without any additional losses, or like you have tried to add some like soft constraint losses, but still it was not working?
So we didn't manage to make it not make mistakes. So the way we use it is we sort of turn the generative variability a bit from a burden into a strength. We just say generate. We sample with nuclear sampling and create something. And if the something doesn't fulfill the basic test, we just backtrack and say, do that last step again because it's not working out. And of course, at some point you have to stop. But if you ask it 10 times, then your chance of getting a valid answer are pretty big.
But I was asking about like more trainings, like phase. What you try to do at that point? Like what doesn't work, so we know and we don't.
So we at the training phase, it actually doesn't work well. That's actually something that also the DeepMind people found, that masking the transformer to not create the not so cool solutions during training makes it worse for some reason. Nobody really knows why, to my knowledge, but so we didn't dare to go too far in that direction.
Oh, that's cool. Thanks.
Thank you for your great presentation. So I have a question about that. Do you think the method will actually work for other structures in the city? For example, the roads, the flyover, the trees? Because I noticed that many of the structures and buildings are actually segmented out and reconstructed individually. So maybe will the roads and flyovers and all those structures will have a scalability issue because we can't really segment them out like
Yeah, there you're definitely right. This involves having a say manageable complexity or extent, of the geometric shape. It also involves in several steps the feature extraction, but also the prediction discretization of the coordinates, which of course gives you this discretization interval and a sort of an uncertainty bound. So I don't think you can simply say, I do this for the whole road network and it will work. You will have to put in some intelligence how to chunk that up into pieces as well.
So you still need to be chunked to
there will have to be some level of chunking. I can't predict what that will be, but I mean, where do you stop, right? You can say reconstruct the entire highway net of the US in one piece. This doesn't look realistic, right? So it's of course all connected to each other, but nevertheless, it's just too big. Also, the geometric structure is very weak, so I'm not sure it would even be a good idea. But this is, of course, a hard part, especially with road networks and river networks and these linear network structures, that they're a lot harder to chunk up because they don't consist of individual sort of things, little distinct objects.
Thank you.
Right, thank you for the nice talk. I like the idea of regressive like polygon transformers. So like the polygon itself, let's say we have a number of points. So to form polygon, clearly order matters, right? So, but in transformers, there are traditional encodings which make transformers permutation, let's say, sensitive. So I think these two things are somehow contradictory to each other. So like why? So have you tried like transformers without traditional encodings?
So you mean use the permutation variants and basically, well, I mean, the point is if you predict the vertices in random order, then you need an additional representational structure to afterwards tell you what is connected to what. If I only give you 7 points and don't tell you the ordering, then you actually cannot make a polygon because there's a combinatorial set of different ways of linking them up.
So basically when training the model, you always have to like fit those points in certain orders.
Yeah, the representation is such that when you look at a face, you actually walk around it in whatever counterclockwise order. And that's how you create it. And that's, of course, also how you create it for training. You can always do that with a polygon. It's not like there is a say, pathological case where that wouldn't work. It is a restriction. But if you just predict a bunch of points, then you have actually not yet predicted a polygon. I'm not saying it's not possible, but you would have to have an additional explicit way of encoding the edges.
So I'm interested if augmenting your training data with synthetics helps in this sort of problem space.
If you have realistic synthetics, almost certainly yes. You would have to, which is sort of borderline feasible, but not completely obvious, you would have to have a LiDAR simulator that creates really realistic data. It's not so much in terms of accuracy of the individual point, but in terms of how many points are dropped, multiple returns, occlusions, the ray drops on bad intersections, all that. It would have to be sort of very close. Again, I'm not saying you can't do it. If you really learn how to use the Helios simulator as best you can, and you have a really good collection of CAD models, then you can probably do it. The question is how relevant it is unless you can go completely synthetic and also generate the buildings. Because if there is a city in the world that has this quality of urban models as a training target, then usually it has been laser scanned recently, right? Because if the geodata department has the power and the resources to create a CAD level model of the entire city, then they almost certainly have regular laser scanning campaigns too. So I think to really make this synthetic, which is certainly a good idea, you should have something that generates building models synthetically too, and not takes the real models and just generates LiDAR for them.
Thanks. Next question. So you mentioned the adaptive polygonal mesh, right? So what difference between the adaptive polygonal mesh with Wireframe or CAD model?
Well, what the difference between a mesh and a CAD model is?
Yeah, you adaptive polygonal mesh, right? I see your slide, right? So
I mean, the polygonal mesh is less high level, it's less structured. It depends on what you call a CAD model. It's certainly not something that you can, like these meshes here, they are still a soup of polygons. You can clean them up. There are actually algorithms, there are routines in professional software out there on the market to make almost watertight models watertight, but it is a pain. So they are not completely watertight because they're not generated by intersection, but one by one. There's also, of course, the constructive solid geometry aspect. So you don't build those out of solids, and certain things like parallelism and so on will be imperfect. So it can also be that a surface is actually split up into two parts, although it could be merged. we cannot absolutely exclude it. It's hopefully unlikely if the thing learned its job, but it is not at the level of CAD models as an operator would draw them by hand. There is still a difference between a structured mesh and a true solid-based CAD model, I would say.
Okay, thank you. So let's start conducting.
Now maybe we'll all go close this session together.
Some missions opportunities. So the evaluation metrics are important. So we use a few evaluation metrics. So the first one is the average corner offset, ACO, just the average offset between predicted corners and ground truth corners. And the smaller offset indicates better quality of generated models. And we use corner precision, edge precision, and corner recall, and edge recall, and we also compute F1 accuracy for corners and edges. So another important metrics is called wireframe edit distance. So we adopt from this ICLR 2021 paper, and it's a variant of the graph edit distance. It measures how many elementary graph edit operators are needed to transform predicted wireframe to ground truth wireframe. So here, those figures show the process. For instance, as you can see here is, for instance, A is a predicted result, and the F is a ground truth. So how many steps it takes to transform the predicted result to the ground truth? There's cost. We call it, WED, right? So we start with edge corrections, for instance, here. So these edges, we move these edges to here. Actually, see, so we call this edge correction. This is one cost. And then we do the vertex matching. We found, this vertex here, and it turns out will be here in the ground truth. So we do the vertex translation to this location, and then this graph becomes like this. So we have redundant edges here. We delete these edges. So there's a cost associated with the edge deletion. Then we get this, then we add two edges here. There's a cost associated with edge addition too. So the final cost will be, the EC plus VC plus ED plus EA. And we also do normalize the WED. So we compute a WED empty. WED empty means from nothing. So you convert from none to a ground truth wireframe model. What's the cost there? So then we use normalize the WED number as a metric. And if the WED equal to 1, indicates we need to create a wireframe model from empty result. If equal to 1, which means your detection is low sense, right? Because even you detect something, but you still need the cost from low detection to ground truth. Okay, so if a number is 1 and also if WED greater than 1, which means you include you include a lot of redundant edges. You need to delete those edges. And when WED equal to 0, which means the reconstructed wireframe model is identical to the ground truth, which is a perfect score. So for we raised $10,000 for the winners, and the first place is $3,500, and second place will be $2,500. Third place will have 2. For third place, they will have $1,200. For honorable mention, we have 3. They will get $500. We thank for PopSmart for sponsor this competition. And so this is the competition result. And there are 12 teams participated in the competition. And the first place will be is from Yu Zhou Liu, Lin Jiezhu, Han Qiaoye, Xiang Gao, and Su Han-sen from Institute of Automation Chinese Academy of Science. They use height map plus 2D corner height map. I think after this one, they will have a binary network. You know the details from the binary network. I think the author is here, so I will also prepare for this paper certificate. I like to give it to you. Okay, yeah. Yeah, come here. Yeah. Thank you. I have the picture. Yeah. 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 Okay. And second place, I think is Hongxin Yang, Si Yuchen, Yu Jun Liu from University of Calgary and Jimmy University. I think it's because of visa issue, they cannot come here. I think they will do online presentation right after the first speaker. And they use initial edge direction guided methods for the building construction. We also have e-certificates. Okay, we send e-certificates to the. Or mail the paper certificate after the event. Yeah. So the third place, I think they use this color detection edge proposal method. They have we have two third place. So I think they are not here. I think it's because of visa issue. It's Jia Hao Zhang, Qi Liu, Yu Cao Dai, Le Hui Zixiang Pei from Northwestern Polytechnical University, and Hong Ye Hou, Fan Yudu, Jia Xingren, Yu Xuanjiang, Xiaobing Zai from Xi'an Jiaotong University. And we have the honorable mention. We have three. Is Fu Haisun, Yin Liang Zhang from Shanghai Tech University, and Qiao Hao, Ting Han, Du Xingzhu from Jimmy University, and Sun Yeshan University, Wei Junwu, Tian Rui, Bali Ria, Gao Guang from PopSmart. Okay, so this is the building 3D team. I think Sang Hong, he did a great work. He managed the public board evaluation, a lot of stuff. But because of visa issue, he couldn't come to this workshop. So I just print this result of competition. Without further ado, we invite the first place speaker, to give a winner talk. Actually, he is also not from the team, but he just present for the winner team because they couldn't come, somehow visa issue. So yeah, but please come. I will open your slides. Here is this one.
Yes.
I will share screen. Okay, so share screen is this one. And we turn on your this display. So which duplicate slash show before this one or? Yeah, duplicate. Oh, now it's now. Oh, yeah, now it's good, right? Okay. Yeah, please.
Hello, everyone. My name is Dian Tao Tu. Today, I'm here to present on my colleague Yu Zhou Liu. He could not be here in person because of the visa issue. It's an honor to present our team and share our work with you here. The rest of the team, including Ling Jiezhu, Han Qiaoye, Xiang Gao, and Shu Hanshen. I would like to start by expressing my gratitude to the organizer of USM Sandy workshop. Thank you for putting together such a wonderful event. Now we move on to the core of today's presentation. Traditional wireframe reconstruction methods reconstruct wireframes from point clouds. Some of them first detect edges and then connect them into detect corners and then connect it into edges. That's the first line. And while other methods directly detect edges from the point clouds and obtain the wireframe from the post-processing, and that's the second line. Where our methods, you reconstruct the wireframe from height maps with 2D to 3D corner detection and edge classification. That's the third line. The motivation for reconstructing building wireframes from height maps including 4 aspects. First, due to the data characteristic of airborne LiDAR point clouds, there is no roof plane occlusion, and restoring 3D roof reconstruction structures is possible. Second, for 3D object detection, there is a large search space, and turning it into 2D will simplify the problem. Third, for point cloud-based methods, the memory consumption is large, so we usually downsample the cloud in the 3D backbone, and some information is lost. With height maps, memory consumption is less, and the point cloud information is more comprehensively utilized. Lastly, with the 2D height map as input, the usage of a mature DETR-based network is possible. We call our method as BW Former, which is short for Building Wireframe Transformer, and this is the overview. Firstly, we project the 3D point cloud into 2D height maps. BW Former first detects 2D corners and initialize the 3D corner queries with 2D positions. Then we predict the 3D corners with a transformer network. Finally, with the predicted 3D corners, we generate edges by connecting every 2 3D corners and selecting the valid edges to form the wireframe. We first introduce the 3D corner detection module. Directly detecting corners from sparse point cloud is difficult because the search space is 3-dimensional, so we project them into 2D height maps to narrow the search space. However, this projection makes some 3D point cloud overlapping with each other. For example, the point in the yellow circle here. There are 2 different 3D points, but after projecting, they have the same 2D coordinates. To address this problem, we first detect 2D corners and then lift them into 3D space with different heights. This strategy simplifies the 3D corner detection task and yields superior performance. On the left side is the detailed structure of the 2D and 3D corner detection model. On the left side is the 2D detection model, and on the right side is the 3D detection model. For the 2D corner detection model, each pixel in the image serves as a query for the transformer decoder and differs in their positional embeddings. The heat map with the possibilities of each pixel is predicted from the per pixel query with an MLP. With non-maximum suppression, the top M pixels are selected for the 2D corners. For 3D corner detection on the right side, the query consists of content queries and positional queries. The positional queries are initialized from detected 2D corners. The first 2 dimensions of the queries are initialized with. Did the microphone stop? Yes, it stopped. Hello, hello.
Oh, it's go. Okay.
Okay, okay. For the sorry, where am I? For the positional queries, they are initialized with the detected 2D corners, and the third dimension of the queries is the height dimension, so it is randomly initialized. And in the 3D corner model, there is a deformable cross-attention layer. The reference points in this layer are the 2D positions, and the height offset and corner labels are predicted with 2 MLPs from the content queries. Finally, we predict whether the corner label is valid or not and obtain the valid 3D corners. With the 3D corners, the final step is to combine them into edges. We cast the edge detection task as a binary classification problem. We exhaustively connect every two corners to get candidate edges. For each edge, we obtain its query by combining the two positional embeddings of its endpoints and passing through an MLP. Then the queries are fed into a transformer network with a classification head. Finally, we get the label of the edges indicating whether it is valid or not. The building wireframe is reconstructed with the valid edges. The training loss of our BW former contains 3 parts. The first part is the 2D corner prediction loss. The 2D corner detection is a binary classification task. It classifies whether a pixel belongs to a corner or not. So the ground truth label is obtained by projecting the 3D corners into 2D, and we compute the binary cross entropy loss. The second part is the 3D corner prediction loss. We compute the L1 distance between the predicted 3D corner and the ground truth. The third part is the edge loss. It is the binary cross entropy loss between the predicted edge label and the ground truth label. Here, we demonstrate the quantitative evaluation results of our method compared with other SOTA methods. And the last line is the BW former. From the table, we can see that BW former has superior corner recall and edge recall performance. It shows the adaptation ability of BW former to sparse 3D point clouds with more complete reconstruction. Here are some qualitative evaluations of our method. We can see that BW former can precisely reconstruct complicated loop structures. Here are more results. However, our method also suffers from some short points. For example, the missing or inaccurate corner and edge detection. In the red box, it's the edge detection. It's an error. And in this red line, there is a missing edge. Our code will be available at GitHub, and you can scan the QR code to access it. Also, you can directly ask questions about this project to the first author, Yuzhou Liu, for the further discussion and cooperation. That's all. Thank you.
Want to take any questions now?
Yeah. Okay. I can answer some simple questions.
Would anyone like to, does anyone have a question? Okay. Maybe we can just thank our speaker again then, and if you have questions, you can follow up with the program.
Right, thank you. So, stop share. So, next speaker will be online. So it's Hongxin Yang. So I think she need to share Xinhong Yang, yes. Okay, I think you, okay, yeah, now it's come.
Okay, hello everyone. First, I would like to briefly introduce our group. My team members and I won the second prize award in the first workshop on urban scene modeling. We are from the University of Calgary in Canada and the Jimmy University in China. Second, we extend our gratitude to all the organizers for hosting such an interesting competition. Now, let's proceed to review the competition requirements. The task is to input a point cloud and generate its corresponding wireframe file using the various methods, including the machine learning and deep learning approaches. So let's review some closely related 3D wireframe reconstruction methods, specifically point to roof and the building 3D, presented under ISPS 2022 and ICCV 2023. So this is the process of these two methods can be summarized as flows, predicting corner points and performing the agent linkage operations. But Recently, a new advanced method introduced at the CVPR 2024 has attracted our attention. This method inputs the point cloud along with the many initial edge entities by passing intermediate heuristic steps to generate the wireframe directly. However, the requirement for the initial edge entities leads to a search space explosion problem. Additionally, in cases such as missing corner points in the building 3D dataset, the traditional method may be not effective. However, the edge regression-based method provides a more reasonable solution in this series. So, to address these issues and avoid using a large amount of labeled data, we adapted the concept of self-supervised learning and implemented a pre-train and fine-tune for roof wireframe reconstruction. So guided by the edge pointer identification. So we can see this is the picture. As shown in this picture, the whole process is divided into the two parts, the pre-train model and the fine-tune model. So in the pre-train model, we can see this picture. We used the mask autoencoder for the self-supervised learning as described in the ECC 2022 to obtain the pointwise future. And then these obtained pointwise futures are then input into the step B and the step C to remove redundant edges and generate the final wireframe model. So last, to avoid the search space explosion problem existing in the initial edge entities, we introduced an edge pointer regression model to generate the initial edge direction, which help us to reduce the problem of the search space. This approach attempts to use a finite number of 129 edges to generate the final wireframe models. But it is worth mentioning that our proposed edge regression loss. We can see this the picture. So in the first the picture, supposing the lines 1, 2, 3, 4 represents the edges of a wireframe model, and the read broad point P is any point in the input point cloud. So in this case, the objective is to predict an offset that brings the values P plus offset close to the nearest line. So the first step is to calculate the distance between the point P to the lines 1, 2, 4. These operations regress the point P to a specific edge. And then if we use the traditional smooth LE loss to calculate the distance between the shortest the distance D1 and the predicted offset, it can cause an error condition. Theoretically, when the values of this loss approach to the 0, the point will be all assigned to the line 1, which will cause the many points to be clustered in the same or nearest position. We can see the middle picture. Specifically, supposing there are 3 candidate points, candidate point 1, candidate point 2, and candidate point 3. These 3 candidates are projected onto the line 1 and masked as the green points, projection point 1, projection point 2, and the projection point 3. So this is the losses between these 3 projection points, and the points P's projection points are the 0.16, 0.157, and 0.149, which are very close to 0. So this will cause the clustering indicates that the many points will be grouped together. So to address the problem, we need to edit a construct that is minimize the distance between the candidate points and the projection point to ensure the candidate point can be assigned to a specific position on the line 1. Then we can use the radical 3D technique to fit this the edge point and determine the initial edge the direction. This includes the concept of our proposed step A. So let's move on the step B, edge parameter regression and matching models, and the step C, edge non-maximal supervision technique. So in the step 2, we use the edge regression model comprised of 4 dedicated MLPs. That is edge confidence scores, edge direction offset, and the edge directions, and the edge lines. These MLPs are used to regress their corresponding edge parameters. The obtained edge parameters are then compared with the ground truth edges to measure the edge similarity. We can see the last slide. Here we use the 3 indicators, includes the distance between the 2 lines and the edge lines and the edge directions. These 3 items will be embedded into the bipartite massing model to measure the similarity of our predicted edge and the ground truth edge. Subsequently, the edge-based non-maximal supervision will be will be based the step 2. The edge-based non-maximal supervision is employed to remove the redundant edges on the edge similarity measurement. Here, due to the time constraint, we will only introduce the improved sections of our proposed method, that is the step A. And the other 2 parts, that is step B and the step C, will be referred to the CVPR 2024 approaches and will not be discussed in detail here. So next, we present a demonstration of the experimental results using our proposed competition method. We can see that the last row of our experimental results, it indicates the effectiveness of our approach, showing that the predicted well-free models are very close to matching the ground truth and the point cloud structure. So finally, thank you for your attention to our competition method. If you have any questions, please feel free to send us an email to discuss further.
Thank you, Hongxing. We have 2 minutes for questions.
Okay.
So I'll ask one question. This is sort of foreshadowing the next challenge, but did you spend any time thinking about how you might modify this for the case where there's even bigger holes in the point cloud? Like, do you think that causes a problem, or you think it would be okay?
So the question, yeah, you said the big, right? Big cloud, right? So you measure
Big holes in the point cloud.
big hole, yeah, big hole in the roof, you know, whether your method will work or not. So some data missing, right? Some big hole in the point clouds. So some data missing. So whether this method will work or not.
I think in some context, this method can relieve the condition of the missing point clouds, because you can see this the example, the coin plots are missing, but we can see this is the edge information are existing. So we can refer this the edge information to reference the edge parameter. I think in some context, this method can relieve some missing corner points. Will bring the discuss.
Okay, thank you very much.
Okay, thank you, speaker. So we move to next session, which is another challenge. So I will. What's this one? The
same.
Yeah, this one.
Yes.
Yeah, but we need to share the
Zoom.
Zoom. Yeah.
Yes.
Yeah. So. Oh. Okay. Share screen. And use this one. There we go. Cool.
Okay, so thanks everyone for joining to hear about our S2 3DR challenge. So fundamentally, what's the problem we're thinking about here, right? We have a set of ground level images, and we would like to construct some representation that's going to allow us to easily read off semantically significant measurements. So a concrete example of this could be, say, we have this, images of a house. Someone wants to replace their gutters, and you want to know how many feet of gutters do I need to order to replace this. And the idea is to be able to go from pictures to some representation that would make this query trivial. So to be concrete, in this particular example, that would be sum up the length of all the red edges in these wireframes that we've extracted. So to be even more concrete, this is images to wireframes. Now I keep saying images, but images these are people's homes. So there's some sensitivity to this, even though these are the exteriors of homes. So there's this tension between the desire to get results and have images and enable these refinement techniques and all the things people want to do, and yet at the same time we want to preserve privacy. So we hope to come up with even better solutions in future iterations, but our solution for now was, rather than release images, we released other modalities, semantics, depth, the outputs of our SFM pipeline, to allow people to kind of make progress while still protecting privacy.
Yeah, and also like in order kind of to compensate for this, like we try to produce as many things as possible, but also like kind of stay in the realm what is possible to get like during the like inference time. For example, we have also like wireframe and human modelers like modeled all the house, but we cannot provide like information from this. I mean, we can from training set, but not for the test sets. Like for everything which should be like kind of obtainable now, and we also have kind of like also like proprietary model here, which actually detects some like house specific semantics, which is like super important for this like wireframe estimation, like apex point and other stuff, because otherwise it would be even worse to do this. And this is like these two guys are actually us both, like, and we were like in both kind of roles, because we really want to have like as best results as possible, but like we also care about privacy. So we'll see how we can do this like better next year. Yeah.
So concretely, these are the inputs that we provide for contestants. So you see on the top row, this is the output of some off-the-shelf model trained on the ADE20K dataset. This is really good for doing things like modeling occlusions, but you can see that the house and building classes just cover the whole house and don't give you very much information at all about the internal structure. That's why on this second row here, we give you the output of an internal segmentation model that we call Gestalt. And that has a lot of these fine-grained house parts, like, for example, these point classes at the ends there, which are the eave endpoints, and these line classes going along the edge of the roof, which are, ridges, eaves, rakes, and also the fascia on the front there. And then in addition, we provide a metric depth estimated by a monodepth network. This obviously is noisy, has problems, so you're going to need to do something to correct that. And then we also release the output of our internal SFM pipeline, which gives, pretty accurate point clouds, but still have these holes in the roof and these other issues that stem just from the geometry of the situation, that you're trying to reconstruct this very large object while you're standing on the ground and you just don't have a very good view of the roof.
Yeah, also wanted to add, like, this is, I would dare to say something which is better that you can obtain with like open source things. like maybe it's like actually I'm doing also other workshop image matching thing, and there would be duster talk. Yeah, sorry for this. Yeah, so what I would like to say is that like this is kind of state of the art what we can obtain. Like maybe the new like CVPR 2024 method would be this, but like not really much. And like the thing that you don't have point cloud on the roof is like because you don't see much roof on the photos. For example, you see like part of the roof on this. Okay, you see actually nothing. Here, yes. So I do see it, but so like but like idea. So like if the house is really high, like you have like this thin line, and this kind of makes things even worse. So this competition is probably a bit more challenging, or like a lot more challenging than the building 3D competition. Oh, okay. So doing. Okay, like while Jack trying to fix the thing, because I can go over like price. Like however, the company we both work at, it has sponsored this workshop and competition. We have like $10,000 first prize, 7 and 5 for second and third place, and we have some discretionary prizes of 3,000, like for those which we believe like maybe their solution is like not the best on the leaderboard, but it's something which we and like other people can learn from. So yeah.
Yes, and not only their solutions, but also some people provided very valuable analysis, which we also wanted to reward. So then on the next slide, we have the names, right? Yeah. So if everyone's been watching the leaderboard,
but maybe we have also metric. Let's see.
Oh, you're right. Yes. Okay. I jumped the gun a little. So first, we'll describe briefly our metric. So I think Risheng already did a very good job explaining this wireframe edit distance, but this is just another view here. So this is trying to explain the various steps. We have a second example here. So the idea is we first start out by matching the vertices. We do this by computing an optimal transport plan. Then each of the vertices has to move to its match location. That produces some cost. We then have a fixed cost for vertex insertion and vertex deletion. And then finally, the edge insertion and deletion.
Yeah, also foreshadowing a bit. So like this is a great metric for things which are like roughly correct and like to rank them. But when things is like super hard to do, it turns out that this metric, which I think is like state-of-the-art metric, like people haven't come up with something yet. And maybe after this challenge, someone, maybe you would publish new paper, maybe we about how to do the better metric. And this is like a little bit foreshadowing.
Yeah, I would say it's a good metric. It maybe has some vulnerabilities, we can say. Yeah. Okay. All right. So without further ado, the winners are these three. So we have Kocho Lin in third place. Yes. Kunal Kanai in second.
Yeah. Also, like as a building 3D challenge, unfortunately, he could not come because of visa issues. And that like I think we as a community should like do something about this. It's like crazy. And but luckily, they first place in a like very last moment come here, Dennis Razumny at ETH Zurich. Like,
yes. Yeah, and he really jumped on a plane like at very short notice. So we're very, very glad that he made it here.
Yeah. And we have also like 2 discretionary prizes for actually people who've like provided analysis and like very detailed, like not just write up of solution, but what they tried and like what they struggled with and like how we can actually improve this for next year. So like discretionary prizes go for Serhiy Ivanov from Ukrainian Catholic University, Lviv, Ukraine. Yes. And Wen Zhao Tan and Wei Han Li from TU Munich. Unfortunately, they also could not join us, but thanks them.
Okay, and then, yeah. Yes, of course. Got to shout out the awesome collaborators. This is a project that's been more than 2 years in the making. Started out when Tolga and Jenner and Dai and Hansha joined us at Hover to work on some research, and we produced the original version of this data set. And now we've come back with this much larger team to, give you this version. So let's take a minute to thank all the other organizers who. Okay. And here.
So here are like first place, Denis Razumny from ETH Zurich.
Yeah, and sure. All good? Oh, okay, you probably should also add this thing from Mike.
Where is it?
Like,
But it's here now.
oh yeah, okay.
So can you hear me?
If there is
On the Zoom?
sound on Zoom?
Can go.
Okay, hi everyone. So let me present this solution. Oh, it's not shared? Oh, yeah. Stop sharing. Maybe I'll share my whole screen.
Maybe just full desktop or something. Yeah, that's good.
No, but still, so it's good. It's good. Okay, so as was already explained, there are many inputs in this task. There is like Gestalt segmentation, there is standard segmentation, there's molecular depth. But unfortunately, there are no RGB images. There is no real depth. There are no satellite views. So most of the methods that you saw today, they cannot be really applicable in this task. So in our solution, we just use SFM point cloud and the Gestalt segmentation. So with the task-specific ones. And we don't use any deep learning, but we propose like a very strong baseline, which we believe can be used further to improve kind of the state of the art. So we start with vertex prediction, where we take the point cloud and we project it to every view. So essentially, we just project every point in the point cloud to all visible views, and we compute a distance transform to the closest vertex label in the Gestalt segmentation, this task-specific segmentation. And then we just select those which have like an average distance below some threshold to this Gestalt segmentation. Then we also have some density-based filtering, where we want to keep only those points which have enough support. Essentially means that in their neighborhood, there are enough other points which also are labeled as potential vertex points. Then we also have some more tricks, but I'm not going into details because of the lack of time. So now we have a set of points, but of course, just based on the definition, we have dense points, like we have more points for every vertex because we keep only points which have enough support. So we need to kind of cluster the points. So we apply k-means, but as you know, k-means needs the number of clusters. So we find the number of clusters by iteratively increasing one by one the number of clusters, and we stop until two closest clusters are below the threshold. The threshold is set to 2 meters, and there is a reason for that, because on the test data set, as you can see, for all edge types, the minimum distance is 2 meters. So it's actually impossible in this data set to have like a smaller edge than this one. And here you can see some examples. So mostly like the projection of the found vertices, it's correct. Usually it is projected back to the real Gestalt labeling, which is very accurate. But unfortunately, since the point cloud is very sparse, even though it's semi-dense, but especially on the roof, there are many points which are missing. And also there are not so many views. Actually, there are just 2, 3, 4 views. So many parts are not visible. So unfortunately, this vertex prediction, it is precise, but it doesn't have high recall, unfortunately. So around 45% of vertices are predicted. There's some more examples here. And also we have an edge prediction module, which is based on a similar technique that we sample possible combination of edges, sample points in between them, and we also project them in every view. And in every visible view, we compute the average distance to the closest edge label in this task-specific segmentation already given by the dataset providers. And then we choose those edges which have with a distance below the threshold, which means in all visible views, they are projected to this segmentation. Let me just quickly to talk about the metric. So the metric has 5 terms: vertex translation, insertion, deletion, and edge insertion and deletion. But it has several shortcomings. First one of them is that it has some pre-registration, which means it wants to make the predicted set of vertices and the ground truth one have the same mean and standard deviation. But this turns out to be a problem because, for example, in this example, the vertices are predicted correctly, but many of them are missing. So then the mean is shifted, and as you can see, it makes the error larger. So especially like this first term, the vertex translation gets higher. Another problem is that there are many vertices of like irrelevant parts. So here you can see that, for example, this thing on the left, it's like, it's not important for the final result, right? Visually, it's the same structure, even if you remove them, but it changes everything by a large margin. And also with the further matching, like if you move the vertices a lot to another location, then the matching is wrong, and then everything gets wrong. So it's very important to kind of have like a precise center of gravity of the estimation. And also the problem is that like missing vertices are penalized, which means it's always better to predict more vertices. Like at least if you predict less, then you need to predict something because you pay the price anyway for the translation. You also pay price for the insertion. So we also show that actually the best strategy is to repeat the same vertices. So you just clone them until the point that you have the desired number of points. And in our case, it's to achieve like this the expected number of points. And actually, the best solution, as I'll show later, is to always predict 25 points. It might seem like a magic number, but it's kind of point where like most dataset samples have this number of points. And also another one is that predicting edges is actually not a good idea. I think probably most of the probably all winning solutions, they don't predict edges because it makes sense to predict edges only once you have like a very good estimate of the vertices. Like you need to have this distance of wide distance like close to 1, and the best solution was around 2. So it's like we are really far in this task to predict edges. So like it's not a good idea, and maybe it's also the problem of the metric that it needs to be improved. And also the last kind of shortcoming is that the edge deletion is measured by the length of edges given by the predicted vertices, whereas the vertex edge insertion is measured by the length of the ground truth vertices, which means that the fully connected graph solution would actually be a very strong baseline. And imagine that you know the ground truth number of points, and you just predict the same points like in the origin, and you connect all these points together. So it's like a fully connected graph. Then the edge deletion cost is 0 because you just delete 0 length edges. The edge insertion is also 0 because like among the set of all possible edges, you have your correct edges. So it's also 0. Vertex insertion is 0, vertex deletion is 0. So all terms except of vertex translation are 0. This is like a very good baseline. It's actually, it achieves like 1.3 distance, whereas the best solution was around 2. So it's a strong baseline. And also like there are some other takeaways that, for example, like if it's better to predict more vertices than less, because if you predict more, you also pay the price of edge insertion. If you predict less, you pay the price. So actually this solution, which I show here, this one-line solution, would win the challenge with this magic number of 25. It would really win the challenge, but actually I found the solution like after the deadline. But the one which won the solution, actually, it's very close to this one. So it's actually just like the number of vertices predicted by the presented methods and this like fully connected graph with them. As here you can see some ablation studies. So this SFM solution with vertices and edges, like if you had edges, it's almost the same solution, but actually it's better to, as I said, to repeat and clone vertices. So like if you repeat them, you have like a much better solution based on this like expected number of points. And then it doesn't make sense to predict edges because the matching is completely messed up in this case. But as you can see, the one-line solution, like the fully connected one, achieved the best results. And I think it's mostly because of the shortcomings of the metric, which needs to be improved. So I'll talk a bit now. So actually, the submitted solution is this one line with like our predicted number of vertices, but it would have been even better to just predict this magic number 25. Yeah, so and the leaderboard actually changed in the last hours because I came up with this one-line solution really like 6 hours before the deadline. So yeah, the main takeaways is like we shouldn't predict edges for this task yet because like we're still far. There are many vertices which are not visible, many parts of the reconstruction which are not visible. So actually we probably need some diffusion-based model because we still have like something we don't see. There's nothing in the ground truth. Like then we should repeat the vertices for this particular implementation of the metric. And for example, the pre-registration usually makes it more complicated. Like you can see that it actually decreases like it makes the score worse. Yeah, so it's a strong baseline, but I think an even stronger one would be to actually learn a solution, learn like some neural network which predicts the number of points. And if it predicts the ground truth number of points, or at least close to that one, you would actually have a really, really strong baseline. So how to improve the metric? So first of all, I think it's we shouldn't match vertices. Because I think the structure is given by the edges, not the vertices. Vertices are just, you know, like if you just predict vertices, you don't see much of the information. Edges are more important. And then we should probably actually match those edges. So here in this example, like if we just match vertices, like this part would like completely be a wrong solution because like there's another one, you don't have those edges, you have another edge, but it's like a visually pleasing solution. So I think we should match and we should actually allow like several to one matching. Like we should allow like to match these two edges to this one and so on. Yeah, and then probably we should actually compute the metric only based on edge insertion and edge deletion, no vertices, because then it actually would make all these solutions which predict on the vertices obsolete. They would have like the worst score. And yeah. And then also cleaning the data set because like we have many like this unimportant, irrelevant parts which change the scores a lot on the current metric because like they have the same insertion deletion score, but they actually don't make the solution any better. It's like the same structure almost. And yeah, the conclusion is still like the data set and the challenge that actually like creates this interesting task. And I think there should be more work to be done to kind of improve the task and solve it in full generality. So I hope this baseline would help with that. And yeah, I think we should start with redefining the metric, cleaning the data set, and maybe like augmenting with full building reconstruction, not only the roof, and training some more methods. Thank you.
Thanks so much for your insightful analysis. No, please come. Yeah. Okay. Do we have any questions from the? Okay. Well, let's thank Dennis again. Thank you.
Just to check, am I audible?
Yes, you are.
Okay, thanks. All right. So, so I'm Kunal Chilani. I'm from Chalmers University of Technology, and I'll present my solution, the geometry-based approach to building roof wireframes. A very interesting analysis by Dennis. I mean, I noticed some of the shortcomings of the metrics while participating in the challenge and coming up with solutions, but not to the extent that he did. So really kudos to him to actually realize that like a one-line solution would have won the challenge. Also sad to hear that a bit that could have ended up in the first position. But anyway, so yeah, here's my submission. So as mentioned, the input to the challenge is general segmentation, a domain-specific segmentation, gestalt, monocular depth from a sparse set of known camera viewpoints, and also a 3D points obtained from SFM for the house structure. And the task is to predict the roof wireframe in a metric scale. So we break down the task of predicting the roof wireframe graph into first predicting the set of vertices, which are the corner points of this roof wireframe. And once we have the corner points, then we would like to formulate which of the edges should be connected between these points. Like Dennis, our approach is also completely handcrafted, and no learning has been involved. Mostly to establish what kind of a baseline this would form. So moving on to vertex set prediction, our approach is essentially based on first identifying these 2D corner points, these 3D points in the camera images. So we identify the 2D vertices, and these 2D vertices are associated with the class information. For example, the top points here are the apex vertices, while these are eve endpoints, like Jack had mentioned earlier. And these, we then combine the 2D corner points from multi-view to essentially formulate the set of 3D vertices. And this class information flows from the 2D vertices down to the 3D vertices, which later on allows us to estimate the correct set of edges. All right, so our vertex set prediction is done in 3 different parts, and then we finally merge all these sets of vertices. The first part is triangulation. So we triangulate 2D vertices of same class, visible in different views. We use epipolar geometry to remove the outlier triangulated pairs. For example, here in this image shown, we triangulate this apex point with this apex point, resulting in this 3D point. However, different combinations of these 2D points would be eliminated because they would not follow the epipolar constraints. However, due to irregularities in the data, there are points remain even after removing pairs not following the epipolar constraint. And for that, we remove points which lie far away from the house structure or the SFM points associated with this house. By the way, the epipolar geometry comes from the known relative pose between the cameras. The advantage of this step is that the triangulated points are very precise. However, the disadvantage is that not all 3D points are visible in 2 or more than 2 views. So the second way of predicting these 3D points corresponding to the 2D points is using monocular depth or scaled monocular depth. So we're given monocular depth as part of input. However, this is at an unknown scale. We project the SFM points in each of these known camera views corresponding to the monocular depth, and use the depth of these projected SFM points to scale the monocular depth appropriately, resulting in properly scaled depth images. The advantage of this approach is that it makes it is available for all the detected 2D corner points. However, this is imprecise because monocular depth estimation itself has noise, and it is grossly incorrect in cases of occlusions. For example, here it's occluded by trees, this house. Now, this can be handled using the general segmentation, the ADE20K segmentation, but we do not do that in our approach, sort of thought about it pretty late. The third step or the third way of predicting the vertex set is to intersect the back projected rays from the camera center to these 2D corner points with the structure of the house. So we have these different camera centers, and we back project these rays through the 2D corner points detected and see where they would intersect with the structure of the house. By intersect, we basically select the closest point. In case of multiple closest points, we select the one that is close to the camera. And this also gives an estimate of the 3D position corresponding to the 2D vertex. The advantage again is that this is also available for all detected 2D vertices. And this is a good approximation when the provided SFM structure is almost complete. However, this is grossly incorrect when there is a missing structure of a part of the house, which is there in many cases in the data. Once we have these three different ways or three different sets of vertices, 3D vertices, we merge them. We give priority to the triangulated vertices because they are observed to be more precise than the other set of vertices. And this gives us the final set of predicted vertices. And all that remains is to predict which of these pairs of vertices form an edge between them. So coming on to adjacency prediction or edge prediction, our edge prediction pipeline is a two-step process. The first one is checking the direction viability of the edge, and the second one is checking the projection viability of the edge. And I'll talk about these two now. So moving on to direction viability, this stems from the idea that most of the edges in most of the data sets or data samples that we saw, most of the edges were along one of the major wall directions. So the assumption here is that the house is rectilinear and there are two major orthogonal wall directions. And we observed that most of the edges, not all, lie along one of these major wall directions. So we first predict the major wall directions. To do so, we project all the 3D SFM points onto the ground plane and do a robust ransack-based line fitting on that, which gives us these red inlier points or one of the wall directions. We choose the other wall direction as the one perpendicular to it and lying on the ground plane. So we have the two major wall directions, and we have observed that most of the edges lie along one of these wall directions. We then choose an edge and see if it's viable. So this edge lining these two apex vertices would not be viable because we have observed that apex edges do not have a vertical component and they mostly lie along the horizontal direction. While this edge is viable because one, it lies in the horizontal direction, and two, it is along one of the major predicted wall directions as well. So we pass all the direction viable edges onto the next step, which is the projection, which is to check the projection viability. This is same as what Dennis presented, that we project the 3D line segment corresponding to an edge in the known camera views and see if this edge has, the 2D edge has support with the appropriate segmentation along the line. For example, this red line, this red edge does not, while if we choose this green edge, then this has support of the expected segmentation along the in the 2D image. So we classify this edge as a true edge. So after classifying all edges through the direction viability and the projection viability, we have our final set of vertices and edges. Here are a few success cases where the green ones are the ground truth points and the blue ones are the predicted points. And in many cases, we see that they're pretty close to each other or close to every green point. In almost all cases, you have, or in most cases, you have a blue vertex. And the red edges, which are the predicted edges, also overlay with the ground truth edges in many cases. However, this approach obviously has several limitations and failure examples. Dennis pointed out a lot of them, mostly associated with the metric. But one important thing is that it's reliant on this 2D vertex detection, which is the first stage. And in many cases, that itself is prone to failure, like multiple or missing detections, which ends up in no prediction close to, for example, all these ground truth vertices. The other obvious failure case is when you have incomplete structures, which is there in several samples. Here, for example, this part of the house is missing in structure, and once you back project the rays, they actually intersect with these noisy points. I mean, we try to remove those, but still, in many cases, you can't really get rid of such points, and this is a limitation of the current approach. Some interesting observations are that the triangulated points are really accurate and should be used whenever available. For example, 63% of the triangulated points are within 25 centimeters of one of the ground truth points, which is rather accurate for this method. While talking about dependability of these triangulation, we see that in 36% of the ground truth vertices, we have a triangulated point within 25 centimeters of it. So in like 36% cases, a triangulation is available, which allows us to triangulate those many points at least rather accurately. And one suggestion is that even if like a learned approach, which would be much more robust at doing this task, is built, I think it would make sense to have these triangulated points as part of this learned approach. Yeah, that brings me to the end. Thanks a lot for listening, and I'd like to also thank my supervisors, Thorsten Sattler and Frederick Kahl, for interesting discussions on this problem. And also the organizers for having such nice organization on Hugging Face throughout. So thank you, Ali. I can't seem to hear you if there are any questions. Let me know in the chat if I should stop sharing and if there are no questions.
Duplicate your view, duplicate your screen. Oh, no. I think, you don't haven't collapsed this one. Yes. Yeah.
Okay, and hello everyone. I'm Yujia from ETH Zurich, and today I'm going to present our work point building. Sorry. Yeah, and point building, reconstructing buildings from airborne LiDAR point clouds. So the motivation of this paper is to transform airborne LiDAR into the polygonal mesh of buildings, and we leverage the aerial survey data for architectural modeling, and we bridge the gap between the raw point clouds input and practical and usable models. We have faced challenges like diverse building designs and low and varying point density and incomplete coverage. As for the meshes, the traditional triangular meshes only contain the small triangles, and while the adaptive polygonal mesh can have the faces with variable vertices, which can offer greater shape flexibility. So the adaptive polygonal mesh is our reconstruction target. So for typical polygonal mesh file, it contains the vertices and the faces. So we split the modeling into two separate parts. The first one is vertex modeling, and then as the face modeling given the vertices. We train two separate transformers to do this task. called the vertex module and face module. We first turn the vertices into a sequence for transformer, and we sort the vertices by the z coordinates first, and then y coordinates, and then x. We then turn the faces into a sequence as well, and we sort the faces by the smallest index in the face. This is the entire architecture for the design method. For the vertex module, it operates by predicting the sequential vertices conditioned on the input point clouds. And the face module, it creates the face indices sequentially as well. The vertex module is in an autoregressive style. It combines a sparse CNN for extracting the point cloud features and transformer decoder to create the vertex sequence. And the face module is also in an autoregressive style. It is a transformer-based encoder and decoder. It sequentially generates the face indices. After we trained these two networks, we can start to generate the vertices and faces. For both parts, we have some specific rules to ensure the valid prediction. Like for the vertices, the stopping token appears only after an X, and Z, Y, X should not decrease. And for faces, the token cannot directly follow a same token, and so on. In order to further enhance the reliability of the prediction, we run multiple times instead of one time, to avoid some invalid predictions like the missing vertices, missing faces, missing walls, or invalid walls. We test our method on the dataset of Zurich City in a large region. Here's a visualization of generation process. The vertex is generated from bottom to top one by one, and the face by face also from bottom to top. Here we show some results in larger scale in some other regions of Zurich. We can see the performance is quite well. Here we show some comparisons with some existing methods. In our data set, we have many like thin structures or overhangs in the data set. For these features, some other existing methods are very struggling to reconstruct these parts because they are designed to reconstruct some compact or watertight models. But for ours, we can successfully reconstruct these thin structures. Here are some concatenative results. We can see our methods performs very well on the vertices prediction and edge prediction. And some other metrics also confirm our good performance on the surface reconstruction. So to conclude, we do the 3D polygonal mesh reconstruction from point clouds. And central to our method is an autoregressive model. And we use the iterative processing to further enhance the model's reliability and accuracy. So thank you for your attention.
Thank you, Yujia. We don't have questions, just next speaker. So we
Hey everyone, I'm Anand from Sharper Shape and going to be presenting the Eclair dataset. It's an aerial LiDAR dataset for semantic segmentation. Yeah, there's generally still scarcity in availability of large and diverse dataset, especially those captured by ALS LiDAR systems. Yeah, part of the reason is due to high capture costs. There's also two other alternatives, LiDAR systems, one from photogrammetry methods. But yeah, these rely on local image descriptors, making them vulnerable to changing lighting and weather conditions. There's also mobile LiDAR systems, which is useful for self-driving applications, but generally it lacks the coverage that one can get from ALS systems, and also the point cloud density uniformity is a bit different from ALS systems. So yeah, ALS systems does help with these drawbacks from the other systems, and it's more uniform density of point clouds. And yeah, data collection can be done in areas that can't be easily driven around. Hence, these systems are ideal for urban planning and surveying applications. So Eclair is the dataset covers an area of about 10 square kilometers. It has 11 semantic classes. 4 of them are non-object background classes, and the rest are object classes with a clear focus on the electrical structures. There are 4 classes from electrical-based objects. The data was captured in Espoo, city of Espoo in Finland. Yeah, coming to more specifics, the data is available as 100 by 100 meter tiles in LAS format. Each point has intensity, number of returns, and return number, along with the color information as features. The non-object classes are ground, vegetation, noise, and unassigned, and there are object classes, 4 of them, which are electrical line-based, and others are buildings, fence, and vehicles. So the classifications for this dataset have been generated by fully automated processes by another in-house model. They're then manually assessed by a team of data experts, and they categorize the tiles into 2 distinct categories. One is labeled as ground truth. So if there are no misclassifications in the particular tile, or if the misclassification is less than 10 points, we label it as ground truth data. And if the errors are more than 10 points, then they are labeled as pseudo labels. Overall, there are 1,246 tiles in the dataset, and yeah, almost half of them are ground truth and the other half are pseudo labels. Coming to the benchmarking, we have trained a ResNet model using Minkowski engine sparse CNN. The interesting part in this dataset is that a lot of the object class are less than 1% of the dataset in terms of point count. This is also similar in many other ALS LiDAR datasets. So yeah, what we observed from the table there is that ground truth, just using the ground truth tiles doesn't lead to good convergence, but adding pseudo labels led to quite a significant increase in the model's performance and helps mitigate this long tail annotation problem. There are also more ablation studies in the paper based on loss functions, the features used, and network architectures. There's also class-wise analysis of performance across these models in the paper. Some qualitative results here. Generally, we observed that buildings and vegetations are quite accurately classified. Similarly, are the distribution poles and wires and towers as well. But the major failure cases are building rooftops. They're often misclassified as ground. Same with vegetation very close to vehicles. These are the major challenges that the model currently facing. Concluding, the dataset allows for large-scale benchmarking of existing point cloud semantic segmentation approaches. The long tail annotation nature of the dataset poses a good research challenge. In the future, we also need to benchmark with more models and newer architectures that are available. And we also plan to extend Eclair to support instance segmentation in the future, and also to add more volume of data in terms of area coverage. That's it from me. Thank you.
Thank you.
Good afternoon, everyone. Welcome to our session. I'm going to present DL3DV, which is a large-scale scene dataset for deep learning-based 3D vision. As we know, Observers is a great dataset, right? And it contains more than 10 million 3D objects. However, 3D object dataset cannot actually capture the complexity of the real world. As we know, real world have a lot of spatial information contained between different objects. But we do have scene dataset. For example, latitude dataset, MIPNO 360, DTU. For existing scene level dataset, they suffer from different problems. For example, the first problem will be they are limited in scale. For example, as we mentioned, latitude dataset under MIP MIPNO 360, they are less than 1K. Another problem they suffer from is because of lack of diversity. For example, real estate, ScanNet++, they are more focused on indoor scenes. However, we know real world have contain variety of scenarios. For example, large-scale buildings, and we have indoor supermarkets, garden, and different level like scenes. So our DL3DV dataset is not only have much larger scale, which we contain TK scenes, and well as we have much variety of the real world scenarios. Here is a snippet of the what is DL3DV 10K looks like. As you can see, it covers different buildings in different landscape, and some of them are captured by the drone, which will contain a lot of cities building, and some of them captured by the commercial phones, which is we cover markets, museums, gardens, coffees, restaurants, and different areas. What you may wonder where we get those datasets, right? So we actually collected those datasets from USA, Europe, China, and those datasets we provide more than 10K video at 4K resolution, and we also provide camera poses for everything. Those will be a graphical distribution of different indoor and outdoor scene from each locations. Then we also have several key features. As you can observe here, how can we describe our scene diversity? We classify it into 16 primary POI locations. For example, you can see in this pie chart, they cover natural, outdoor, also cover like business locations, sports, and autonomous service, and different like hotels and residential, and medical service, education institute, those kind of the first level primary POIs. Besides, within this primary POI, we also have the secondary. For example, for the natural and outdoor scenes, we have square, we have street view, we have like farms, forest, mountains. We have like different lakes and campgrounds and high trails. Then you may wondering what kind of complexity we covers. We actually annotated for each scene based on 4 level, indoor and outdoor. We also classify into different level of reflection and transparency, based on how the percentage of the pixel covers and how duration in the video. Besides, we also classify into different light conditions. Some of the condition will be indoor light, which is most likely human created light or artificial light. Some of them are natural lights, some of them are mixed lights. This is all the things we have for dataset. If you are working on multi-view reconstruction, 3D scene generation, or generalizable nerve, and also 3D Gaussian sublime or other representations, you can feel free to download our dataset. And we also have a posters in the coffee chat. If you want to know more information about our dataset, feel free to come to us. Thank you.
Thank you. So now next speaker ready to set up computer. We take the later time.
Yes.
Yeah. It's showing the wrong one. Just wait. Wait, so it's fine. Just wait to send it. Okay. Well, hello, everybody. Thank you very much for attending this presentation on our research work, Simplicity. So the purpose of this work is to generate lightweight building models from airborne LiDAR data with respect to the following objectives. Accuracy, first of all. Indeed, the produced model should constitute a faithful approximation of the data. They should be composed of a low number of vertices and facets. Meshes should also include some properties such as watertightness or manifoldness, and the algorithm used to generate such models should be robust, efficient, and scalable. Existing approaches only partially fulfill those objectives. Okay. For instance, model-driven reconstruction techniques cannot be used to reconstruct the buildings of arbitrary shapes. Shape assembling techniques, for their part, often rely on a 3D partition of the space which are computationally complex, while learning-based methods do not always enforce geometry guarantees on the produced models. In this work, we propose yet another shape assembling technique that is based on two key ingredients. So first of all, a 2.5D planimetric arrangement that generates a concise and watertight building models from LiDAR data. And second, a regularization procedure that simplifies the obtained models while enforcing geometric regularity such as collinearity or orthogonality between the facets of the mesh. Our pipeline departs from semantically classified LiDAR point cloud and a building footprint. We first extract a set of planar primitives from the point cloud using a state-of-the-art technique. Then we construct a planimetric arrangement. Departing from the planar shapes, we first extract a set of 3D line segments standing for plane-to-plane intersections or high discontinuities in the point cloud. Those line segments are projected onto the horizontal ground. Combined with building footprints line segments, they are used to feed the kinetic data structure, which generates a complex, decomposition of the 2D space into convex polygonal cells. We then assign a unique plane label to all cells of the partition. This labeling procedure is formulated as a POTS model with a complexity term that penalizes complex roof structures. However, if we take a closer look at the obtained roof structures, we observe some geometric flaws. So the next step of the pipeline then consists in simplifying this planimetric arrangement and enforcing its geometric regularities. So to this end, we first simplify the 2D partition by collapsing all edges in the partition whose length is less than a certain threshold. Then we form pairs of near collinear or near orthogonal segments edges in the partition, and we solve a global optimization procedure in which 2D coordinates of the partition are adjusted so that all selected edges get exactly collinear or orthogonal. So regularized 2D roof structures can now be lifted to 3D. Since each roof section is associated with a plane equation, we construct a full set of 3D vertices that is needed to represent all of them. However, we note that some 3D vertices that share the same X and Y coordinates may be close to each other along the vertical axis. When this is the case, we merge such vertices so that this way we can reduce the number of vertices that compose the final mesh. However, this operation breaks the planarity of the obtained roof sections. So to recover facet planarity and guarantee a valid polygonal mesh, we solve yet another optimization procedure. Our goal is to find not only the new Z coordinates for all the vertices, but also new plane equations that satisfy planarity constraints on all roof sections. We complete the building model by adding a set of vertical walls so that in the end we obtain a watertight and closed mesh. So qualitatively, our model produces building meshes which contain significantly less vertices and facets compared with state-of-the-art techniques. We can observe that some shape assembling techniques such as kinetic shape reconstruction or geoflow may approximate multiple plane concurrency. Something got wrong with the microphone, I guess.
Well, so this multiple plane concurrency can be approximated. Well, it's approximated by an unnecessarily high.
Oh, sorry.
Does it work?
You know how technology being. So they're coming back now.
I don't think so, but well, your screen is empty now.
Nope. Mine is good. No, I think it's good. It's working.
Okay, okay.
If anyone has one question for the speakers, this would be a good time. It's getting back now. Right. There we go.
Yeah, okay, okay. I'll let you.
Okay, back on track.
Yeah. Okay, so yeah, so before this interruption, so I was about to say that well, some shape assembly techniques such as kinetic shape reconstruction or geoflow may approximate multiple plane concurrency by an unnecessarily high number of vertices, which is not the case of our technique, and regularity is also enforced in our pipeline, contrary to other state-of-the-art pipelines. So quantitatively, we also compared meshes produced by our pipeline and the aforementioned state-of-the-art techniques on 3 different data sets where both LiDAR data and reference building models are available. So it can be seen in this table that our pipeline achieves similar accuracy levels, comparable running times, while delivering meshes with significantly less vertices and facets, and geometric guarantees such as water tightness. So we also plan to release our pipeline as a web service in some near future. So you are invited to visit my poster if you have questions or if you are interested in this work more generally. Thank you for your attention.
Okay, so good afternoon. Sorry for this whole mess. I am Giacomo D'Amico Antonio from the University of Eindhoven. I will present my paper on unsupervised anomaly detection in traffic trajectories. So what we did in this work was focus on how to detect anomalous trajectories in traffic in a way that could be explainable and easily deployable in any context across the world, basically. We focused on the vision-based approach, but with some caveats. And to this goal, we proposed the U-Trend framework. It's a three stages framework that allows us to provide an explainable and precise estimation and classification of different type of anomalies that can occur in traffic. So in the first stage, we obtain the calibration of the camera that's observing the scene, and we use it to work the camera videos to obtain the bird's eye view videos. In those bird's eye view videos, we detect and track various agents moving across this intersection. The agents are cars or vehicles in general, pedestrians and bicyclists. And then in the third stage, which is the most important one, we are able to model the intersection as a graph. We learn the connection between nodes in this graph, and we are able to detect and classify anomalous trajectories. To do this, we start from the bird's eye view of the intersection. We obtain a semantically segmented map of the bird's eye view. We split the map into patches. And each patch corresponds to a portion of a lane or of a portion of the middle of the intersection. And to have precise patches, we use the ITF standard, which is an European standard for geographical coordinates of lanes and other topological component of an intersection. It is also possible to do the same by semantically segmenting the lines that represent the lanes in a camera view. From here, each patch is considered as a node in this graph, and we learned the connections between the nodes by observing about 12 hours of footage through the uTrend pipeline. In fact, when we detect an object and we have its bounding box in the bird's eye view, we are able to assign that object to a patch of the intersection by just doing intersection over union. So just seeing which patch is the most closer to the bounding box of the object. What we obtain in the end is a representation similar to this, where each node is connected to other nodes with direct links. So we have three main attributes that define a node: the set of nodes from which you can go, starting from a starting node, then how many or which kind of agent can be allowed in the specific node, and also the average time that an agent spends in a specific node. And at this point, each anomaly can be classified by using very simple rules, which takes this framework apart from the old school expert system. The rules here are very simple and very explainable. So an agent is, for example, stopping unlawfully in the middle of the intersection if the amount of frames in which the object is in a specific node is higher than the average time computed in the training phase. Same thing goes for the improper zone and wrong turn classes. This is an example of the visualization that we obtained with uTrend. We can see that the car 11 that you can see stops in the middle of the intersection for longer than it's supposed to be stopping there, and uTrend correctly classifies this as an anomaly. But what's interesting is that in the same video, there is another anomaly happening. And while car 11 is driven by one of my colleagues, car 13 was just on the street doing unlawful movements. And here you can see that he moves on the wrong lane and drives in the opposite sense of direction. And the uTrend correctly identified this anomaly, classified it correctly, while it took us like 5 minutes of looking at that video over and over again to see what was going on. So this kind of framework is really powerful in expressing and explaining why an action is anomalous, and it allows the user to extend the type of anomalies that it's detecting. And it's really easy to implement, deploy in the real world and in different scenarios in a completely unsupervised manner. So you don't need labeled data or anything of the sort. This concludes my presentation. If you have more questions or you want to know more about this, you can check my poster in the poster hall. Thank you.
Yeah. Thank you. Hello, everyone. So my name is Simon, and I'm here with my partner Lasse, and together with our co-author. What? Oh, thank you. Yes. Right. Yeah, that's fine. And how do I go to next?
You have to click on the screen.
Like this.
Oh. Okay, there it was.
Oh. We're here to present our dataset, which is called the OpenTrench 3D, which is a photogrammetric 3D point cloud dataset for semantic segmentation of underground utilities. So we're going underground now, which is a little different perspective from some of the other data sets. And we're from Aalborg University in Denmark. So first of all, let's have an overview over the data set. So we have collected 310 fully annotated point clouds. It consists of 528 million points in total, and they are distributed in 7 different areas. Where 5 of the areas we have water utilities, and 2 of the areas we have district heating utilities. On this image, we can see some of the areas where we have collected this data. So we have different rural areas from Copenhagen, from inner and outer Copenhagen. And I don't know if you can see the cursor, but here we have an example of water utilities, and we have some district heating utilities. And we have 5 different classes, which we'll see in a moment. On average, every point cloud has around 2 million points. So we benchmarked our data set with 2 different benchmarks. So one in which we trained on 4 of the water utility areas and tested and validated on the 5th. And the other benchmark, we train on all the water areas and evaluate on the fine-tune on one of the district heating areas, and then evaluate on the last district heating area. So in the first benchmark, we can see that from the table here, we can see that we achieve a pretty good performance on the main utility class, which is the water and district heating class, which is I think it's a nice result that we can actually achieve a pretty good performance. And we see that we use PointNext, PointVector, and PointMetabase as our benchmarks. And we can see that PointVector and PointMetabase performs best in this case. Here in this image, we can see some of the classes, or our classes. We have our main utility, which is the water or district heating. We have some other utilities, which can be gas or telephone or fiber, internet, and so on, all kinds of different utilities. Then we have the trench class, which is more like a background class, some inactive utilities, and some MISCs, which can be leftover stuff residing in the trenches. In the second benchmark, we test on the water areas, or we train on the water areas, fine-tune on one of the district heating areas, and evaluate on the last area. I think here we see some pretty nice results regarding fine-tuning. So if we just train on the water areas and test it directly onto the district heating, we can see the results here in the yellow. But if we fine-tune with just a couple of examples from the district heating area 1, we achieve a much better performance from just fine-tuning on 1, 5, or 10 examples. And we can use this finding so we can actually extend into other utility classes without having to annotate like hundreds of new point clouds. We can just use our pre-trained model and fine-tune it on a new class. And here we have some qualitative results where we compare the pre-trained model with a model fine-tuned on 1 sample and one fine-tuned on 10 samples. And yeah, I think it's pretty clear, especially in the last row here, that we get a much better performance from fine-tuning on 1 and 10. So I think I'm about to run out of time. So yeah, thank you for your time, and feel free to scan the QR code or visit our poster in the poster session. Thank you very much.
Thank you. So our next keynote speaker is Lower Slavery because he is very busy. He will have a lot of talk in half an hour, so we don't have maybe a lot of time for Lower. Instead, I will play a video which is left from the game.
Oh, sorry. I can try and end a little early, so there's Q&A. Anyway, we'll see. Oh, is this like something I can plug in?
You can just plug that in directly.
Okay,
Because you guys understood that.
Oh, thank you, John.
Thank you.
Unmute? Sure, let me unmute. Yeah, I'm gonna unmute. And I'm gonna turn my video too. If I can. Oh. Okay, good. Okay. So this is so cool. I feel like I'm losing my voice a little bit. Okay, well, we'll see how well this works. So this is, it's great to be here. Thank you so much. I'm going to be talking, let me use this mic. Sorry. Oh, I need to share my screen. Oh yeah, Zoom, thank you. That's really important. Good. So I'm going to be talking about a new data set we're building called Megascenes. New large-scale data set. Okay. Resume slideshow, let's try that. Okay, I'm having some trouble. There we go. Oh, it's not showing up there, is it? Let me try one more thing. There we go. So by the way, if you saw my talk in the image matching workshop, this is going to be almost the same talk, so you can just see one of them. Okay, but I'm a big architecture fan. I really love cathedrals in particular. I love looking at them. I love reconstructing them in 3D. I remember when I was a kid, I saw this book called Cathedral by David Macaulay. It's this great book that talks about, oh, if you want to build a cathedral and you're living a millennium ago, how do you do it? Well, it talks about all the tools you need to build it, all the different craftsmen you need, wood cutters, stone cutters, etc. It tells you how you need to dig a big hole in the ground or several big holes and fill them with blocks cut to the right shape. You keep building and building, and at a certain point, you have to construct this big wooden wheel and hoist it up so that you can pull huge blocks to the top of your cathedral. It's just very interesting, and it really goes to get you thinking about, okay, you have these buildings, and every part, it doesn't just look nice. Every part has a function. The shape of it has a function. It's much deeper than the surface level geometry. And I probably don't have to, I'm preaching to the choir here. There's a lot more to, buildings than just what's on the surface, right? Of course, maybe they look nice too, but there's a function to them. Another book that I really love is this book called The Story of Buildings, with illustrations by a master cutaway artist called Stephen Biesti. And I find this picture really compelling. This is a diagram of the Notre Dame Cathedral, famous cathedral in Paris. And it just shows it's so richly detailed. You can see the outside of it, you can see the inside of it. You can see okay, the last talk was about trenches and showing stuff that's inside. You can see inside the roof, it has a little exploded view diagram. You can see people milling around, so you can see the scale of the space and how people use it. Everything has labels and names of things, and these names I find very attractive and romantic, like the flying buttresses and the vaults and the timbrums and the archivolts. There's just a language to it that's really deep and interesting, and rich. And so I don't know. Sorry, you can't see behind my Zoom, but I've been thinking about, okay, I've worked in 3D reconstruction for a long time. What I really want to do, though, is go beyond surface level reconstruction and really reconstruct rich 3D models like the ones that I just showed you, okay? And moreover, I want to be able to do it from open data. I don't know, you can use Street View and all sorts of scanning, or whatever fleet of airplanes Google has. but I'd really love to be able to do this. It would just be so poetic to be able to do this from just data that's on the web, like this crowdsourced vision of how to reconstruct things. Now, in computer vision, we've made some progress toward this, I'd argue. We're very good at reconstructing geometry. We can take unstructured images like tourist photos of the Notre Dame Cathedral and reconstruct their camera poses using structural motion, reconstruct nice point clouds, and I love this. I love reconstructing point clouds. And we can go further, like we can go further than point clouds. We can go towards more photorealistic reconstructions. So this is not published work, and this is not even my work, but so Sungyo sent me this nice video of his own results on 3D reconstruction for internet photos. I think this is the best like quality 3D reconstruction for internet photos I've seen. This is like Gaussian splatting based. I think like there's a paper called Nerf in the Wild that I used to use to illustrate this, but I think this is even better. Anyway, maybe I think he'll post it on archive pretty soon. It's beautiful, but I think it lacks a lot of the underlying semantics and rich kind of contextual structure of that diagram. Okay, so we can reconstruct lots of things. We have 3D reconstruction as a tool in our tool belt in computer vision. So we can like find everything there is to reconstruct and reconstruct it and build models of everything in the world. And then what? What do you do once we reconstruct everything? Like, at a certain point, are we finished with like the 3D reconstruction project because we've reconstructed the whole world? And I think, so I'm going to talk about a few answers to this question. And the first answer is that this is a incorrect premise. Like, we're actually very far from being able to reliably reconstruct everything in the world from images. So I'm going to talk about this data set, Megascenes, in a few minutes, where we reconstruct lots of things at scale from Wikipedia type data. But if you start running things at scale, like any tool like Colmap, like the community's favorite 3D reconstruction tool, if you start running it like thousands and thousands of times, you observe all the ways that it goes wrong. And one big way it goes wrong is repeated patterns and symmetries. So here's a building you might want to reconstruct. It's the St. Paul's Cathedral in London, beautiful, Sir Christopher Wren structure. And if you take a bunch of internet photos of this building and feed them into Colmap, you get a reconstruction, and that reconstruction seems to have the following property. It has a dome-shaped object. By the way, this is a bird's eye view. We're looking down at it. It has a dome-shaped object made of points. Okay, so far so good. And then has a dome-shaped object made of cameras. Okay, all these like black little wireframe pyramids are reconstructed camera positions. And those two domes are nowhere near each other. They should be co-located because the dome-shaped set of cameras is photos taken from the dome. But they're not. And the reason they're not, and there's a lot of messy geometry, like just floating around in weird places. The reason they're not is because, feature correspondence, like the bread and butter of 3D reconstruction, totally went haywire and matched things that it shouldn't have. And this is not just a problem with this one building. Like, people love to build things that have repeated structures, like Big Bens and Eiffel Towers and other things like that. And so this happens surprisingly frequently. And if you want to reconstruct things reliably and you don't want to have to check every single model, then you really care about this. Okay, so this is a instance of a problem in computer vision. It's kind of a philosophical problem of visual twins. If I show you two images of something, how do you know if they are images of the same thing or images of two different things that happen to look the same? Okay, that's a problem that's certainly happens in these architectural reconstructions. And the problem is that if you run feature matching to try and tell the difference, but tell these two cases apart, local feature matching will find lots of high confidence matches between images like this, despite the fact that these two images don't overlap, or at least not significantly. They're opposite sides of a building. They're opposite sides of the Arc de Triomphe. And therefore, there should be really no correspondences, except maybe inside this inner arch part. Okay? So that's bad. And, I'm really intrigued by this. Like, it's a very kind of intriguing question of like, how do you tell, if you see two things that look the same, are they the same or do they just look the same, right? I was working on this visual disambiguation problem. This is like a long, people have studied this a lot in computer vision. When I came, years ago, when I came across this National Geographic on twins, and the subtitles alike but not alike. And yeah, these two people look alike at first glance, but then, if you start studying them carefully, I'm sure you'd find like different freckle patterns and, from the stochastic process. And as twins age, they start to develop differences, more and more differences between them. So like, you can probably see like very subtle differences in the face structure between the pairs of identical twins that I'm showing here. And this article talked about all this and why this happens and why twins are not actually twins, that kind of thing. So you might come across your identical twin if you have one, or you might just come across like doppelganger, so-called doppelganger, which is a person who looks exactly like you. And you might be entertained if you find somebody like that. But in computer vision, it's bad. We don't like these doppelgangers, these so-called evil twins or doppelgangers that are misleading matches, okay? So how do we deal with them? Well, as a person, what you might do is like, okay, how do I tell these apart? Well, I lay the images on top of each other and flip back and forth and then try and spot the differences, like in a kids game, like you see in kids magazines, right? And if you look, they still look pretty similar, but if you look carefully, you'll notice like the sculptures on the face of the building are different. The buildings in the background look similar, but actually there's different buildings in the background. You can kind of see maybe what looks like downtown in one of the images. So yeah, if you look carefully enough, you can spot that they're different. Okay, so we wanted to solve this problem because it was really annoying to us. And we did what you always do, I guess, these days in computer vision, which is you build a data set and then you train a classifier in that data set. Okay, but how do you build a data set of doppelgangers, these illusory matches? Well, it's very difficult because if you set out to do this yourself, you have to train yourself to like tell the difference between two things that look very, very similar, like training yourself to tell the difference between identical twins. So instead, we rely on the wisdom of the crowds to do this, okay? There's this really nice website, which I think is underappreciated in computer vision, called Wikimedia Commons. And this is the like data store behind Wikipedia and other things. It's one of the Wikipedia projects. And this data set this web page has a categorization of everything. It categorizes lots of, every entity that's known, especially every visual entity that people care to write a Wikipedia article about. So it has categories and subcategories. It's like a big tree with some loops, it turns out, annoyingly. Okay, so like cathedral is a category, and under the cathedral category is enumerated all the cathedrals that are on Wikipedia. Okay, and you can look at one of these categories, like the Notre Dame Cathedral, famous cathedral again, and you can see a bunch of subcategories. It's just really richly categorized and annotated data. So you can see historical photos of the Notre Dame Cathedral. You can see a bunch of subcategories, including like love padlocks, some whole subcategory devoted to love padlocks. You can see a category about the great organ of the Notre Dame Cathedral. You can see a subcategory of the shamads of the great organ of the Notre Dame Cathedral, which are shamads, I learned, are horizontally pointed organ pipes, not the usual vertically pointed ones. And so it's just very, I don't know, you could get lost just like you can get lost on Wikipedia, you could get lost on this Wikimedia Commons site. And so how is this useful? Well, it turns out that in certain categories, in certain places, there's subcategories by viewpoint. Okay, so you can look and see, okay, so here's the Arc de Triomphe. It has subcategories of back right views and front right views. So they're labeled by, someone has done the work of labeling them by viewpoint. And that's very useful for us because if we come across like two viewpoints that logically shouldn't overlap, and yet Colmap finds lots of feature matches between images in those categories, then we found doppelgangers. Like they shouldn't overlap, but they do. And yes, we could use things like Street View, but I prefer in this kind of, I'm very interested in like open data. So if we can find data like this on the internet, it's really useful. Okay, so here's some examples of doppelgangers we've mined from Wikimedia Commons, and in total we have about 178,000 doppelganger pairs. So here's some examples from various places in the world where you have repeated patterns. So yeah, what you're looking at is pairs of images that look the same but aren't the same, including things like, two castles that are thousands of miles apart because Disney built the same cathedral to the same castle to the exact same spec in Japan and Florida. And you can find lots of feature matches between them because they're so precisely constructed. Okay, good. And now that we have data, we can train a classifier. And rather than just like blindly classifying pairs of images like stacked into an image sandwich or something, we feed a little bit more information to the classifier. We compute features and matches. So and encode this as input to a network, so it knows which parts of the image match, and then I guess by negative data, which parts don't match. So it can maybe tell, oh, part of it matches, but this other part doesn't. Maybe that's a sign it's not a real match. And then we also use those matches to compute an affine transformation and roughly align the two images in the pair so that it can do like this, spot the difference. It has like visual correspondence between the two images. And then we feed that into just a neural network that classifies them as correct or incorrect, meaning it's a doppelganger and it doesn't really match. Okay, and here's an evaluation. So there's, we did the careful thing. There's no like overlap between the training landmarks and the test landmarks. And here's some results. Okay, so what we're seeing here is a plot of accuracy in this doppelgangers task. Higher is better. Our classifier is that blue bar, that's the highest. Some other baselines are those other colorful bars. And you can see, well, we do better. Okay, first glance you might say, okay, it's going, so the baselines are things like taking the number of feature matches of different kinds of feature matchers and just thresholding. Like if you have more than 100 matches, call it a true match. If you have less than 100 matches, call it a false match. And they work okay, maybe in some sense, like you're getting 86% performance, but you really, okay, false positives, I guess I'll call them, are very bad. When you're going to reconstruct a landmark, you have a match graph with lots of edges between matched images, and even a single bad edge can ruin your reconstruction. So even like 95% is not quite good enough, but it's good enough to do better if you integrate it in. So I guess the useful way to think of this is that we're decreasing the error rate by maybe a factor of 3 or so, like from 15% error to 5% error. And that is really, really helpful. And here's some examples of classified images. So, okay, on the left, you see negative pairs. These are doppelgangers, bad, evil twins. And on the right, you see these are pairs that should be categorized as good matches. And you can see that our classifier correctly can distinguish between these cases, attributing low scores to the doppelgangers and high scores to the real images. And that's nice, despite the fact that these images on their face look very different than these images. So it knows to like discount illumination as, illumination is something that is allowed to change, right? It really should focus on the underlying structure. And it's just because it's been trained on a diverse enough set of data that it knows to do this. Okay. So then you feed this, you just run this as a step inside Colmap. You run feature detection and matching in Colmap. You filter all the matched images using this classifier. Then you run SFM, structure motion, on what's left. And it works quite well on internet photo collection. So, okay, here's an example of a broken Colmap construction. At first you might say, okay, how's it broken? Looks fine. But what happened is it should have the full 360 Arc de Triomphe, but only half of it has been reconstructed because both of the halves have been glued together by wrong matches. After discarding doppelgangers, we get a much more complete reconstruction. Here's another example. This is the Alexander Nevsky Cathedral. Again, so the reconstruction, it actually has too many domes if you just run vanilla Colmap. After running our method, you get a reconstruction with the correct number of domes, which is like 2. Okay. And here's some other results. Big Ben is the worst offender. Big Ben is so hard to reconstruct. It's really annoying. It might not look wrong from this bird's eye view of the Colmap reconstruction. These are all vanilla Colmap reconstructions in the second row, but it's very wrong. And after our method, we fix all of these different models, including this Big Ben. If you were to remove the cameras, you'd see a nice 4-sided Big Ben instead of like a 1 or 2-sided Big Ben. Okay, good. Okay, so now that we have this, now that I'm more confident in our ability to reconstruct things automatically, we can now scale this to all the world scenes and reconstruct all the places that Wikipedia knows about. And so we did that. We created a data set called Megascenes. It has over 100,000 structure motion reconstructions with over 2 million registered images. The data is open and it was just released. We just put it online yesterday. You can start using it if you want to. And it's orders of magnitude larger than a previous data set we made called Megadepth in terms of the number of images and landmarks and things like that. And the way we created this was inspired by this previous data set called Google Landmarks Dataset V2, which is, there's nothing 3D about it, but it was for like landmark recognition or image retrieval. So like take a picture of the Eiffel Tower and recognize that it's the Eiffel Tower, or one of hundreds of thousands of other landmarks. So it's like a large scale landmark recognition data set. They built it from Wikimedia Commons and we did the same thing. We first okay, there we go. So we first have to enumerate all the things in the world before we can reconstruct them. So it turns out this other Wikimedia project called Wikidata is really helpful for that. It's like a knowledge graph. It knows about everything in the world that Wikipedia knows about, and it's like a structured database. So it knows which things in the world are tourist attractions and arches and bridges. So you can query it for, okay, you can do an API call, give me all the tourist attractions from the Acropolis to the Antwerp Zoo, etc. For each of those, it links to the Wikimedia Commons page, which has, again, images. You can scrape all those images from all of the subcategories rooted at that page. And then you can run structure motion. So, and run doppelgangers to disambiguate and get nice structure motion point clouds and registered images and so on. And here's some example reconstructions from the data set. It has all your famous landmarks, like the Notre Dame Cathedral, but it also has like all of your long tail of things that are like local landmarks too. Here's a distribution of scenes by category. So it has a lot of religious buildings. Turns out there's a lot of those in the world. But it also has a lot of other things too, like museums, palaces, fountains, lighthouses, and so on. It's very heavily biased towards Western Europe, unfortunately, but it does have worldwide coverage. This is like a heat map of where the landmarks are in the world, because Wikidata also knows about their latitude and longitude, so we can see where on the map they are. Now, what I really like is we built this great web viewer, which I think I can show. Why not? So basically what this is I'll just load up some pre-loaded ones. So you can along with this data set, if you go to our webpage, you can see this nice web viewer. You can do a auto-completed search for a landmark here. So here's just some examples. Okay, here's the Great Sphinx of Giza, the one everybody knows about from Egypt. Here's another one. I'm just switching tabs here. I just preloaded these. Here's another Sphinx, which is a Sphinx that's in the Louvre. I don't know, plundered or something. Who knows? From Egypt. What is this? This is a outdoor scene. This is the Kapellbrücke in Lucerne. What's the next is, I think this is an indoor scene. This is the Pantheon in Paris. Okay, the cameras load faster than the point. There's the points. Okay, so yeah, we have this nice point cloud of the interior of the Pantheon in Paris. This is, and it has a long tail too. This is I guess, random historic building at a random address, 11 West 54th Street in New York City. So yeah, it's just really fun to explore. Oh, I don't know. Does anyone have a landmark they want me to look up? This is like a nerve-wracking demo time. Yes.
The Epcot Mall.
Epcot Mall. I've heard of Epcot Center. Okay, well, Epcot, yeah. So there's Epcot. Let's see what that is. I haven't quality checked all of these, so yeah, it looks like it didn't do a very good job. This might be a small part of Epcot. Oh, I'm curious what the other places are. Spaceship Earth. Yeah, so many of these reconstructions are kind of small, like long tail kinds of things. There's also different components to see. Is this is not the big ball, but is this the big ball? I think this is the big ball, yeah. I think maybe the official name of that ball is Spaceship Earth. Yeah. Yes. Yeah. I actually preloaded that one. Yeah, so this is a view of I think this is like Seattle as reconstructed from the Space Needle. So you see like a big Space Needle shaped tower here with like cameras going up the elevator and cameras at the top. And this is not a reconstruction of the Space Needle itself, but the city of Seattle around the Space Needle. Okay, yeah, sorry, I should probably go on because but you can play with the web viewer yourself. It's live right now at this URL. Okay, so what can we do with all this 3D? I think there's a lot of applications like better feature matching, better monocular depth prediction. It's just a lot of geometry data. You could train a better duster. You could train view synthesis like 0, 1, 2, 3 because you have a bunch of posed images with relative pose and so on and so forth. So I'm really curious how people use this data. Okay, just some open problems. So, we've reconstructed a lot, but I've made no progress towards the thing I said I wanted to do, which is go beyond the geometry soup you get from structure motion and go more towards semantically rich reconstructions like would be needed for this visualization of the Notre Dame Cathedral. I think one way to get towards that goal of more semantically rich and contextually rich data is, integrate 3D and language, 3D and vision with language. So, learn some, we have vision language models. If we had vision and 3D language models, maybe we could, build scenes that are more semantically rich. So, some of the data that exists on Wikipedia, there's a lot of language data that's associated with the images that we use to build megascenes. So here's just some examples of 3D geometry reconstructed, as well as caption data. So, I feel like ChatGPT, but that knows about geometry might be a good path forward for the community. I also think, we have all these great tools in 3D computer vision like Colmap, but they're not really multimodal. They're sort of like 20th century technology. Sorry, I don't mean to that as pejorative really, but we have such great tools that are not just geometry related. We have LLMs. A simple example is if you feed all the Wikipedia Commons data to Colmap, it includes things like floor plans, which you would think that's the most useful thing for reconstructing a scene possible. It's the best image, but Colmap doesn't know how to parse it. It doesn't know how to match it. So it just throws it away. So if we could somehow upgrade our tools to, sorry, I think something just reset. Okay. Yeah, anyway, so let's move into the 21st century, I guess. Another problem is 3D reconstruction ignores the fact that the world is really 4-dimensional. So things happen over time, like the tragic fire at the Notre Dame Cathedral. Places like Times Square are very dynamic. So we really want to be reconstructing dynamic scenes. So we have some work on this 4D reconstruction problem called neural synchronology, where you can reconstruct a time-varying model of Times Square. See how it evolves over time. But this is still a very open area. Okay, so I think I'm just going to leave with some challenges. So a lot of the reconstruction I showed you are incomplete, like just the inside or just the outside of something. Well, it'd be great if we could automatically create full models of things from internet photos. Semantically rich reconstructions, where things are labeled and it knows the names of things. Transcending this Colmap pipeline so that it knows more about language and other kinds of modality than images. Computer graphics ready models. I think we're very far from having models that can be relit and interacted with in a compelling way, like a Pixar set or a computer game environment. 4D reconstructing things over time and also generating new scenes. I think that's a big open challenge. Okay, so with that, I'll thank you very much. And thank you for your attention. Thanks to the people who worked on all these projects, and thank you for your attention. And I think I have 1 minute for questions, and then I might have to go.
Sure.
Sorry about that.
Yeah, one question.
Please,
Thank you for the question. So I'm just wondering, you mentioned like your method can outperform this comment a lot. So have you tried like link with 3D Gaussian, say you just use your method to get initial point cloud, then followed by this kind of 3D Gaussian, what kind of surface can you get?
Yeah, so that visualization I showed at the very, towards the beginning, I think that is a 3D Gaussian on top of the camera poses you get from something like Colmap. Sorry, I don't know if I can show it. I'll try to.
Okay.
But yeah, so that fly through the Trevi fountain, that's using Gaussian splatting. And so yeah, what would be great is if we could run that at scale on all of our scenes, like have beautiful 3D fly-throughs of all of the 100,000 scenes in our data set. That's something we'd like to do. We just haven't done that yet.
Okay, so
Yeah.
what's the shortcoming?
I don't know. We have to try it. I mean, I don't, it's one of these things you don't kind of know until you run it lots and lots of times.
Okay.
It could also be, computational efficiency. Maybe that we'll have to see.
Okay. Thank you.
Okay, thank you very much. Thank you so much. Thank you. I'll be back for the panel. Yeah.
Yes. So we have one for video.
Planning, energy management, and public safety. For example, by utilizing the results of indoor scene understanding, scientists can assess dynamic indoor environments more effectively. However, existing methods for indoor scene understanding often struggle to balance accuracy and efficiency, especially when dealing with both RGB and depth information. This limitation hinders the application of these methods in real-world urban research scenarios, where real-time performance is essential. RGBD information is complementary. It can improve semantic segmentation accuracy, but it also increases network complexity. Existing RGBD semantic segmentation methods introduce substantial redundant parameters, reducing computational efficiency. Our research problem is, how can we improve the accuracy of semantic segmentation in indoor environments without substantially increasing network complexity while ensuring real-time performance? Asynformal is a novel architecture that consists of three main components designed to address the limitations of previous methods. First, we introduced an asymmetric backbone, which uses a larger convex network for RGB feature extraction and a smaller mixed transform for depth features. This asymmetrical design reduces redundancy and improves efficiency by allocating computational resources based on the importance of each modality. Second, we proposed the local attention-guided feature selection, LAPS module, which selectively fuses RGB and depth features in both spatial and channel dimensions using a learnable strategy. LAPS adapts to the specific characteristics of each modality, improves feature selection compared to fixed attention methods. Finally, we introduced the cross-modal attention-guided feature correlation embedding, CMA module, which enhances feature representation by modeling cross-modal subsimilarity. CMA embeds cross-modal information into the fused features, capturing the relationships between To validate the effectiveness of ACE Informer, we conducted extensive experiments on the NYU V2 SunRGBD datasets. On the NYU V2 dataset, ACE Informer outperforms many state-of-the-art methods, such as Informer-S, FRNet, and PGDNet, while maintaining real-time performance. With a mean IOU of 54.1% and an inference speed of 65 FPS on an RTX 3090 GPU, ACE Informer achieves a better balance between accuracy and efficiency compared to these methods. In conclusion, ACE Informer is a novel and efficient method for real-time RGBD semantic segmentation that addresses the limitations of previous approaches. By introducing an asymmetric backbone, local attention-guided feature selection, and cross-modal attention-guided feature correlation event, ACE Informer achieves high accuracy while maintaining real-time performance. Our method has the potential to significantly impact various urban research problems, such as urban planning, energy management, and public safety. Thank you for your attention. We have shared the open source code on GitHub. Due to visa issues, I am unable to attend the conference in person. If you have any questions, please feel free to discuss them with me via email.
Thank you. This concludes this session. If you have questions, please go to the poster post session, which is in the ARC building. Let's coffee break. Please come back at 4:20 for another keynote speech. Thank you.
Thank you. Okay, all good?
Yeah, good.
All right, so let's restart. So when I was first invited to give a talk on urban modeling, I was thinking I haven't really done much 3D urban modeling for a while. But then I realized that actually many years ago, more than 10 years ago, actually, I worked with people on urban 3D reconstruction. And this first work was an interactive reconstruction. So you see that on the left, you have this very sparse point cloud of a building. And it's actually a very hard problem to actually reconstruct complete building model. So what we did was basically user can define a box and then snaps the point cloud. And on the right, you see that when you have many repeated structures, I think NOAA is actually a big challenge to reconstruct structures with repetition and symmetry. So you are able to reconstruct one structure, like one set of like balconies, and then you basically just drag and drop, and then you interactively reconstruct the whole building, right? So in the end, the reconstruction quality is very high because it's really semi-automatic. And then there was another work that we did. This one's called a structure preserving retargeting of irregular 3D structures. So you see that these are actually 3D buildings, and you're able to stretch, lengthwise and height-wise, and then you're able to get these automatically produce new contents, right? So this was actually inspired by a work in imaging called seam carving. So you can create all kinds of varieties. And the key thing here is that you learn kind of the regularities, and then when you do the stretching, and then have some understanding of what needs to be done. It's not just purely stretching, but sometimes you have a structured repetition as well as you stretch things in different directions. So, and for a while, even though I haven't really worked a lot on urban 3D modeling, but it's always in my mind to think about what are special characteristics of these 3D urban models or urban models in general. So there are a few. So first of all, structure regularity. So symmetry, repetition happens a lot, and also other relational features such as complanarity, and also geometric regularity. This is like more local properties, and this is kind of shared with most of the CAD models, like sharp features, corners, and also the prominent use of parametric curves and surfaces. So you see all kinds of examples here with both architecture and CAD models, cars, chairs, and also CAD parts. So the reason that this is happening, this is the case, is really coming from this notion of the forms or geometry actually follows the way that these things are being used. Okay, this is a very famous concept from architecture, in particular called the form follows function. And just because of the way they're being used, their functionality, that you have this repetition and you have this regularity in these models. And there's another notion, which is, these things are all human-made. Okay? Because they're human-made, there's a lot of criteria that coming from the manufacture process also dictate the way these urban models or CAD models are.
So because you need to serve functions, right? Think of urban models, think of many of the CAD models like cars and vehicles. So we know that not only exteriors that are important, actually the interior is also important. If you think of all the furniture models, right? So if there are only exteriors, I don't think they're actually useful. They can only be visualized, but you cannot really open things up and then trying to find things. So the interior is also very important, as you see from all kinds of examples, including urban models or CAD models in general. Finally, again, as I mentioned, these things are all human-made, and they were usually made by pre-built pieces. There's this thing called a prefab in manufacturing. And these prefab or pre-built pieces can be called like primitives. There are all kinds of primitives depending on what you're building. Now, of course, computer vision, graphics, NLP, we're in a deep learning era. So we keep asking, what are the best neural representations, right? For CAD models or for urban models. So the interesting about 3D is that there's no single representation, that's the representation. So this is actually different compared with images and speech. Without images like a rectangular area of pixels, videos or speech, but with 3D, all of a sudden you have a ton of representations. So what are the best ones? So let me sort of review a bit of a history of different neural 3D representations over time. So I use this year 2019 because something sort of happened in 2019. So before 2019, you had these papers, the PointNet, for example, encode point features for motion recognition, and then you have other models like even generative models using 3D GAN and other representation. You have meshes, you have points, you have multi-view representation, MVCNN, you have also trace OCNN. And then miraculously, I think all three papers from CVPR 2019 all seem to sort of got to this idea of neural fields or implicit representation. So there's three papers called IMNet, Occupancy Networks, and DeepSCF. And then I think these three papers kind of started the era of neural fields, and it flourished. So then what happened then? Sorry, let me actually first just give you a very quick, just like one slide description of this IMNet. This was our work from CVPR 2019. It's a very simple architecture. It learns a coordinate-based representation, specifically there's a mapping from a 3D point XYZ to a status, inside-outside status into occupancy based on a shape code. Okay, so they started with a global shape code and made people have all kinds of variations with the way that you encode your shape. And the architecture is very simple, just a few, this is the modular infrastructure. And then what happened? So in 2020, this happened, NeRF happened, right? So NeRF, everyone knows this work from ECCV 2020. And if you think about a NeRF, it's also a coordinated representation, right? So for IMNet, it goes from XYZ and you get occupancy. And for NeRF, you get XYZ and also a direction of a camera ray, and you're going to produce color and density. So there are quite some similarities, and also NeRF uses MLP, at least the original one. And then what happened? So 2023, I think CGRAPH 2023, 3D Gaussian splatting happened, right? So by now that people know there's a lot of advantages of 3D Gaussian splatting over NeRF, but Gaussian splatting is also a point representation, uses representation for point primitives. So now I want to make actually a point which I think is a very important point. If you think of 3D representation, I believe that NeRF and Gaussian splatting, they actually produce rendering primitives, right? And the goal there is mostly for novel view synthesis. But I'm a graphics person in training. I think about modeling, right? So I think there are actually a lot of issues with the representation produced by NeRF and Gaussian splatting because they're actually not modeling primitives. So what can go wrong? So this is an example result from mobile NeRF. If you actually remove the texture, it doesn't look so great. So it's just a very unorganized set of polygons. So the first issue is it's unstructured. I actually believe that humans reason about the 3D in a structured, highly structured manner. Okay, so these representations are actually not structured, and they're not easily editable and reusable, right? You spend a lot of time producing a 3D thing, you cannot really reuse it because it's just for rendering, just spin and then zoom in, zoom out, right? You cannot really reuse it for other modeling purposes. And finally, I truly believe that the reason you generate something in 3D is not just look at it, it's actually use it to put it in a scene, interact with it in robotics, So functionality is very key. So I believe the true purpose of generating something in 3D is actually to use it, not just look at it. And these models are not very useful. They're not something can easily, do functional reason. Okay. So of course, you see sort of this path of development from, very early works on neural 3D representation. You have neural implicits 2019, you have NERF, and then there's a path of Gaussian spline, and then like, 500 papers a year. So we took kind of another path. Again, we started with IMNet, and then we focused on this notion of learning modeling primitives and especially structured neural representations. So I'm gonna go through these papers, but I won't be able to go through every single one in very technical details, but I'll try to get to sort of the most key points for each one of them. So as I said, it's all started with IMNet, very simple architecture. Again, there's a mapping from a 3D coordinate XYZ to an occupancy using MLPs. So the first question is also kind of coming from my background. I'm a graphics person. I do a lot of structured understanding. I asked the student who did this IMNet, can IMNet be trained to learn shape parts, semantics? Okay. So he did this so well. He just did a very simple thing. He just changed just one thing, and that was it. And that thing he changed was just make the last layer a branched layer. That's the only change to the IMNet. Okay, so that was the thing, because we want to actually learn parts. So, and then he's able to actually learn these parts without any part supervision. Okay, so I'll explain a little bit more detail here. So we ideally like every branch to learn a shape part. Okay, so here you see an airplane, and then you want each branch to actually learn a part. For airplanes, so one of them is maybe the fuselage. And the application that we cast this network in is so-called co-segmentation. So co-segmentation is you have a collection of things. I want you to segment all of them in a consistent manner. Okay, so in unsupervised co-segmentation, we call this network branched autoencoder because it is branched. It's basically changing IMNet with the last layer branched. It just gets trained on a collection of 3D shapes, and it just have this reconstruction loss. Okay, this is the unsupervised way. And if you want to like one-shot learning, you only have to actually just give it a one single shape that has part labels, and then you can train this network to not only get a low reconstruction loss, but also an extra shape label reconstruction loss. You can actually do this just with a single shape, and then that's actually the result of segmenting a collection of chairs with only one shape with part labels. So why does this work? Okay, so if people knew this notion of Occam's razor, it kind of has a bit of a flavor there. So it basically is a compactness. So we took IMNet, we made it actually even smaller. Okay, so IMNet has, I think, 5 layers, and this one only has, I think, 3 layers. And then we'll also have less neurons. So we compact this network, this small network, and then because of the compactness, the network is forced to actually learn consistent patterns. So we actually did a very simple test on this very simple toy example where you have 3 patterns. You have a triangle, you have this cross, and you have this diamond, and then they are placed all over the places in this background. And then because of the compactness of this network, okay, it is forced to learn the actual kind of interpretation of what these patterns are. These patterns are these 3 patterns are arranged at different places. So it's each branch actually learns 1 pattern. So that's very encouraging. We have other examples as well. And then the student took a closer look at what's really happening with each layer. It's only 3 layers, right? We can kind of see what's happening. It's not something really, really deep. It's only 3 layers. So we can see what's happening at each layer. So the first layer seems to learn these linear ramp functions. Okay, it's very clear by gradient. Okay, and then the next one seems to be combining these things. And the next is combining what's happening in the second layer. Because actually the patterns were actually pretty clear. So this is something, if you do like a simple toy example, you can actually discover patterns. So what this did to us was just, hey, it looks just pretty nice, right? So why don't we just make this interpretability explicit? Okay, so we actually force the first layer to learn planes because there's like near fields, right? And then we let them combine. Okay, so that's kind of the key idea for the next paper, which maybe some people know about. It's called the BSP net. Okay, so BSP here stands for binary space partitioning. Again, I love it because I'm again graphics by training. I love to use this like old concept and then use it in a neural setting. So BSPNet actually is pretty much the same as IMNet, right? Because it also has this XYZ and has a shape code, and then it has a reconstruction loss. But what's happening in the middle is that we're going to force this network, the first layer to learn planes. In fact, the first layer, the weights are defining the plane parameters. And the second layer is going to combine the planes into convexes. And the next layer combine convexes into union them, and then so that you can actually construct general shapes. So it's actually, you can say, it's completely interpretable. So BSPNet binary space partitioning essentially learns plane primitives. See, this is kind of, resonates with the topic of my talk. So we started with plane primitives, right? And specifically learns how to best represent a collection of shapes using n planes, and n something you can set. I think most of our experiments, n was 4096. And at inference, you take your train network on a collection of shapes, and then based on input, it's going to select what planes to use, and it's going to approximate your input. And the output is unlike something you produce using marching cubes from a neural implicit field, because it's very smooth and it's not sharp. We want CAD models to be sharp, and then this one has sharp features, and you got to mesh directly without using marching cubes. So that was pretty. It's also a compact mesh representation. That was one of the features of BSPNet. So what's next? So planes are limited, right? So how about we generalize to more general primitives? The next one we tried is quadratic primitives. And also at the time we're interested in CAD models, CAD parts. We decided to work on CSGs. So CSG stands for constructed solid geometry. So it's a very prominent CAD representation for parts, machine CAD parts. So the BSP extension essentially extends from planes to quadrics, and then we add a difference operation, because difference operation is useful when you have this machine parts with a hole, right? So it's better to use a difference operation to carve the hole out instead of using like a union of convexes. And the goal here is to produce compact CSG trees without ground truth tree supervision, because that's harder to obtain. So although this picture looks somewhat different, but the overall architecture, again, is following the same path as IMNet and BSPNet. In here, you take your input, you encode it into the latent space, and you have this primitive. You see all those parameters define quadratic primitives. And then you have a set of curry points, and then you produce these point to plane distances, and then some clever algebraic tricks. You're going to produce point to convex differences and point to difference of union, and then finally these sample points to differences to the shape produced by a difference operation. And then you have your ground truth set up, and then you want to minimize the reconstruction loss. So this is something we call the CapriNet, CVPR 2022, and it's able to learn these CSG trees. So what's nice about having such a structured representation is that you can turn your CSG tree into an open CAD script, and then you can just edit it because it's highly structured, right? This is something you really cannot do with 3D Gaussian splatting or NeRF. So for example, you take this open SCAD CSG script, and then you say, turn this cylinder radius to this, and you're going to give you the result as desired, and then you can also change the outer shape into a box. So this editability is something you get from modeling primitives, not something you get from rendering primitives. Compare CSG tree results and CapriNet results to BSP results. You can clearly see that when you have a part that has a hollow, has a hole, the difference operation is desirable. If you just use union, it's an unnatural tree. However, if you look very closely, these are actually unnatural, right? Because I just need one cylinder to hollow this hole, right? I don't need three things like that. And also this other thing on the left is also kind of redundant, right? There's nothing we could really do about it. This is what the tree gets you, because, well, it gives you a really low reconstruction loss, right? This is one issue which I'm going to resolve just in a bit. And another issue is that even though there's no ground truth tree supervision, you still need 3D input. Okay, so what's the most popular problem at CVPR? It's multi-view reconstruction with sensors or something like that, right? NeRF, Gaussian splatting. So we thought, okay, can we pose this problem of multi-view to CAD So remember I said that I care about modeling primitives. There's too many papers on NeRF and 3D Gaussian splatting. I want to work on multi-view to CAD, right? So this is can we turn something which is NeRF-like, but it produces modeling primitives? So that was the motivation. Okay, so this is very recent work, sparse view to CAD. So the task here is to go from sparse.
You start.
Hello? Just decided not to work. It's better. Okay, thank you. So we're going to start with as few as 3 images, and so that's sparse, and also they're a kind of wide baseline views, so they don't have to overlap a lot, right? So in Contour, a lot of the works you have like a few views that are actually very close by. This one can be very far apart, and our goal is to reconstruct something in 3D, not only just in 3D, but it's actually an assembly of convexes, right? This is kind of a follow-up of CapriNet. And we use differentiable volume rendering to do this without 3D supervision. This is why this is a NeRF-like thing. So it actually produces textures as well, right? So that way you can actually, because it's an assembly of convexes, you can do your editing just as you did with the other modeling primitives. Okay, so some technical details. So overall, if people are familiar with pixel NeRF, so the overall architecture is resembling a pixel NeRF, it's image conditioned NeRF. But there's one change, which is the key change is to replace the density estimation by what we call differentiable primitive assembly. So this is actually the part which is very much like a CapriNet, right? So instead of producing density estimation, we'll produce occupancies that would produce an assembly of convexes, right? So specifically, as you can see, the assembly part is very much like part of the CapriNet. So we didn't have the difference operation in this work because we were focusing on, ShapeNet shapes. Okay, so that was like one branch. The other issue that I wanted to fix was this issues with CSG assemblies. Okay, as you saw from this previous speaker, these are unnatural trees. Okay, so if you recall, the only thing that we did for the CSG assembly learning is have this reconstruction loss. Okay, but this reconstruction loss really has nothing to do with whether the assembly is a good one or not. Okay, so there's no optimization towards how many assemblies, how many parts you use, how many primitives you use. There's no optimization towards whether it's a good or natural assembly or not. It's just a reconstruction loss. So theoretically, there are actually infinitely many CSG trees that will all give you 0 reconstruction loss. So there's actually a lot of ambiguity. So that's like a big problem. No matter how low your reconstruction loss is, your tree may still be very unnatural. Okay, so this is actually maybe a case that can illustrate that. Now, also, if you think about, if I just give you a shape, what is the best CSG assembly? You really cannot tell, right? There's not even a notion of what is the best CSG tree for a given shape. So there's also ambiguity there. And finally, coming back, this is a workshop about urban models. I don't think CSG is actually most suited for urban models. Maybe they're for machine parts, but not for urban models. So what are the other alternatives for CAD representation? So for people who are in CAD, this must be BRAP or boundary representations. So it's a de facto shape representation for general CAD models. I believe it's suitable for machine parts. It's also very suited for urban models. So a BRAP represents a 3D solid by defining the limits of its volume. It consists of vertices, curves, and parametric surfaces. So surfaces intersecting to curves and curves meet at vertices. It's a structured, hopefully also a compact representation. So BRAP is very well known in the CAD community. So then we have this work, which learns to predict a BRAP from a point cloud. Okay, we call it a split and a fit. So why do we do that? So let's say we'll start with a point cloud. In the first step, we actually essentially predict Voronoi boundaries. Okay, so we don't directly predict what the surface patches are, what the curves are, and what vertices are. This is what most other people did, like in complex gen. This is a piece of work from MSRA. The reason we do this is that we want to get the primitives, we also want to trim them, we also want to get their connectivity in one shot, okay? And this is, I really actually love this one because I love to use this sort of classical mathematical concept that kind of comes to use in this very, very modern setting. And it turns out that Voronoi partitions actually serve that purpose. So we're going to take a point cloud, and then we're going to develop a neural network that learns the Voronoi boundary. And the other thing is that if you give me a shape, you give me a BRAP, its Voronoi boundary is unique. You know what to optimize for. There's not like infinitely many Voronoi boundaries that give you the same BRAP. It's a unique Voronoi boundary. So that's the first step. We call it split. And then for every cell, we're going to fit a single primitive, and that's it, because that's the fit step, right? The Voronoi boundaries does the trimming for you, and the Voronoi cell connectivity gives you the connectivity between your primitives. Okay, you get like everything in one shot. If you don't do that, you have to have a network that predicts the primitives. You also have to predict their topology. Okay, so there can be inconsistent issues, right? So this is, I think, a simpler approach by predicting Voronoi boundaries. Okay, so I have a short, like this is only like 1 minute and a half video just to give you a bit more details. And I think the best way to do this is actually just to move the mic to the speaker here. So hopefully it works.
Need to solve 3 questions simultaneously. How many primitives are there? What are the best primitives? And how are they connected? The mixed combinatorial and continuous prediction brings ambiguity during the reconstruction. Our novel split and fit pipeline adopts a top-down approach for BREP reconstruction. It first splits the space into several spatial partitions, resembling a traditional Voronoi diagram, and then fits a primitive within each Voronoi cell individually. The Voronoi diagram not only indicates the exact count of major primitives but also naturally embeds their topological connection. Given an unstructured point cloud, we first compute the Voronoi boundaries of the underlying shape. Then we reconstruct the Voronoi cells through the Voronoi boundaries and perform primitive fitting within each cell. The point cloud is transformed into a voxelized unsigned distance field. Voronoi boundaries are predicted on local voxel grid patches using a UNet, which converts input features into a binary flag indicating Voronoi boundary presence. Finally, we use the Voronoi boundaries to form Voronoi cells and fit a single primitive in each, eliminating the need for combinatorial point assignment and simplifying the primitive fitting to a purely analytical process.
Okay, so that's just a very short video. If you want to learn more technical details, this paper will be presented at SIGGRAPH 2024 in Denver.
Need to solve 3.
Okay, I'm coming to summaries now. I guess I firmly believe that more people need to work on modeling primitives. Multi-view to CAD, multi-view to 3D scene, multi-view to urban models. We need more work along those lines. And then the modeling primitives allow you to edit, right? Because people work on 3D Gaussian and then say, how do we edit that? Okay, they work on NeRF and how do we edit that? Okay, if you're able to directly reconstruct these high-level primitives, then you can directly edit them and reuse them. And also for functional reason, because functionality is very much tied to the structure, the parts, right? Because the functionality actually performed by these parts, especially for something with complex functions. And CS3 and BREPs are structured CAD representations. I hope there are more works on multi-view to CS3, multi-view to BREP, and also generative modeling. I hope Yasu will be talking about it in his talk. So in this talk, I went through these series of works, starting from IMNet to branch autoencoders, and then BSPNet, and then CapriNet, and then in between there's another branch into something called the D2CSGNet, which is an improved version of CapriNet, but due to the limit of time, I'm not able to give you the details. And DPNet, which is differentiable primitive assembly, finally this work on using split and fit for learning Voronoi boundaries for BREP representation. Now coming back to urban, I strongly believe, even though we haven't really tried it, I strongly believe that this BREP using split and merge would work for urban models. May even be simpler because we had some trouble with B-spline surface patches, right? But for most of the urban models, they're mostly planes, right? So we just need to try it. Okay, so I've asked the student already to start working on this. And remaining challenges, this actually echoes what Noah said. Actually, structural regularity, one of the key characteristics of urban models, is actually still very challenging. None of these works that I've presented so far has any provision on producing things that respect regularity or symmetry. Okay, how do you add that as a prior? How do you produce these things? I think that this is possible, but it may not be a trivial problem. And second of all, these exteriors versus interiors. I asked Tom this question. I care very much about interiors. I think we're missing interiors. If we don't have interiors, many of the 3D models are useless because they can only be visualized. They cannot really function the way they do. Okay, so I have time. I have 5 minutes.
Yeah, 10 minutes.
10 minutes. Oh,
Yeah.
good, even better. So I will show you this is the work that will be presented at CVPR on Thursday. So I think there's some potential of reconstructing interiors from a single view. So this problem here is a single view 3D reconstruction, and we'll call this work Slice 3D. So I'm gonna play the video here.
Hello, everyone. In this video, we present Slice 3D, a new way of looking at single-view 3D reconstruction that is a complete departure from conventional approaches.
Sorry, somehow it's not playing. Let me see what's going on.
Hello, everyone. In this video, we present Slice 3D, a new way of looking at single-view 3D reconstruction that is a complete departure from conventional approaches. Single-view reconstruction aims to reconstruct the 3D geometry and structure of an object from a single input image. As one of the most fundamental problems in computer vision, many advances have been made, yet the most fundamental challenge still remains: how to faithfully reconstruct occluded parts from just one view. A natural way for humans to reveal occluded parts is to rotate an object, so that it can be observed from multiple views. Most recent methods on single-view 3D reconstruction first perform single to multi-view synthesis, often using a diffusion model, and then employ differentiable rendering, such as a NeRF, to lift the multi-view images to 3D. But the results obtained often lack details and exhibit various artifacts. One of the key reasons, if we look into the details of the synthesized views, is the lack of consistency across different views. Such inconsistencies are difficult to resolve via 3D reconstruction. In addition to the inconsistency problem, there is an inherent limitation to the multi-view approach for revealing occluded parts. Let us illustrate this using a 2D example of a lamp with a shade, bulb, stand, and base. As we can see, no matter how many camera positions are sampled around it, the bulb still cannot be observed. This is because the camera rays are blocked by either the shade or the base. In our work, we introduced a completely new way of occlusion revelation for single-view 3D reconstruction through slicing. Specifically, we use a plane to cut through a 3D object to obtain one object slice, and then render it into a slice image. Then we repeat this using a few more parallel planes to obtain the second and then third slice images. Finally, we render the last remaining slice into an image. As you can see, these slice images can reveal the occluded parts without rotating the camera. At last, we lift the slice images into a 3D model. With our multi-slice approach to single-view 3D reconstruction, in contrast to multi-view approaches, such as the 1, 2, 3, 4, 5, we obtain better results, especially in revealing occluded parts. Importantly, with slicing in the limit, that is, when using infinitely many slices, we are guaranteed to unveil all hidden structures, while the same cannot be said about multi-view captures. Now let us see what would happen to a 3D lamp. Our method can indeed successfully reconstruct the bulb, while 1, 2, 3, 4, 5 via multi-view cannot.
Okay, I'm almost done. I hope it's hello. Oh, it's working. Yeah. So more details. If you you want to find out, you can go to the paper presentation on Thursday. Again, I really think that again, also a lot of people need to work on in reconstructing, reasoning, locating, mapping of interiors because we mostly live in interiors, right? So there's a severe lack of 3D models interiors. So what I know for sure is that there are 2,300 models from Partner Mobility that are interiors. And the largest one right now is Objectverse and Objectverse XL. There may be some models interiors, but I cannot really count because there's no official count of how many. There need to be more and more, right? Think of you actually interact with them, like the function, you actually need to have interiors. And that's actually a very hard problem. How to acquire that? And how to reconstruct them? And then generating them. I think you can open up a whole subfield of reconstruction, just focusing on the interiors. Okay, so if machine learning or AI is not advancing fast enough, let's acquire them. Okay, so this is a work we did last year at CBAF Asia. We have a robot. Actually, this is only per object reconstruction called active 3D reconstruction. The robot goes in there and opens things up and then scan and close it. Now let's imagine do this at the urban level, right? So what do you do for the very large scale? Yeah, by the way, this is all related to embodied AI and learning by interacting, and it's a perfect problem integrating vision graphics and robotics. At the very large scale, you have drones, right? And then you should have robots, okay, going into a mall, automatically going up and down stairs, and open up all the doors, go into every room, open up every single drawer, scan all of them. So that's, I think, the ultimate thing to do. I think, you know, machine learning or learning to do this, you need the data first. There's actually a lot to do in terms of acquisition. Okay, I'm done. So these are the papers that I've covered, and I also want to acknowledge all the collaborators that I have on these papers. Thank you very much.
Right, if anyone has questions, you're welcome to come on up. And please, other people come in form line.
Thanks, Howard, for this great talk. So I'm just wondering, when you talk about, I mean, it's good to see you really link with this kind of primitive-based modeling with like 2D image supervision. So I can see, I mean, you kind of use a lot of like, you use nerve, you use occupancy field. I mean, I'm just wondering, like, I mean, how fast is the process?
Yeah, it's actually pretty fast. Yeah, it's pretty fast. So I mean, let's take Slice 3D. Slice 3D is not producing primitives. I think it's definitely minutes. So Ali, you can. So how fast is CapriNet? 2 to 3 minutes. Yeah.
Because you still need to do the volume rendering part.
So the only thing that does volume rendering is the DPANet. Right. So I don't, off my head I cannot tell, but it's not like really slow. It's
okay.
Yeah, it's because the primitives, there's not too much to learn, right? It's just only for a quadric, it's I think 6 parameters. We can bound the number of primitives. It's a much more compact model, so it's definitely not very slow.
Okay, so you're not converting into the occupancy field. You're not doing the sampling around the array kind of.
No, we do sample points. The point sampling is just to produce the point to primitive distances for the loss. But what you produce is an assembly of primitives, and there are not that many of them.
Okay.
It's definitely not at the scale of how many voxels you have for your reconstruction.
Okay, thank you.
Yeah.
I'll ask one in the 1 minute we have.
Sure.
So suppose you did have millions of interior videos.
or even ground truth models.
Mhm.
Do you have some, direction? What would you do with that?
Okay, so first of all, if you have these 3D interiors, and I don't see a clear difference between doing reconstruct, learning to reconstruct or generate compared to exteriors. I think it's a very similar problem. I don't see. I think the challenge is actually to acquire that data. I think it's much more difficult in terms of, because a lot of the interiors not even reviewed, right? I mean, you actually need to kind of open it up, right? So there are works, I mean, active reconstruction is when you actually go there and actually open it up, right? But then you have to worry about things like, how do you make sure that the human that does the opening is not obstructing, it's not reconstructed. So that's why robots is better. But then robots, most robots cannot even open all the doors, right? It cannot even do the grasping always perfectly. So there's a lot of challenges. So I think the data acquisition is a challenge.
Okay, let's thank the speaker.
Thank you.
Our next speaker is Yang Su. He is a principal scientist at Wave.
Mute and no video necessary. No video sharing. Yes. Then actually, where is yes, play? Is it working?
Yeah.
Yes, working. Yes. Yes. Oh, thanks everybody for sticking around. It's my great pleasure. Want to thank organizers for inviting me. I do lots of scene modeling. That's why I think I got invited. Although I did a bit of object modeling in the past year, which I'm going to talk about today. So it's about object, not scenes, but hope you like it. On the two topics, very complex CAD models and very loose geometric modeling, starting from the latter. We have seen lots of superhuman AI systems, ChatGPT and others, but 3D reconstruction was superhuman 20 years ago already, when I was a student, for precise geometric modeling. This is really the classic, the ROM project from UW Seattle right here. I was happily involved in the project. So you can estimate precise camera poses and recover precise geometry from the million images from the internet. Or Apple Flying Over 2012 launched, so almost a decade ago. And this is dense model of the texture map done, pretty realistic. This is really 2012 and very impressive. And I call this superhuman because I cannot do that, or likely many cannot do that. You're sitting on a plane, fly over the city for a few hours, come back, given a laptop, they have to make a model, texture map. You cannot do that. They are really superhumans who can actually do this. I saw the documentary. Like really, airplane, few hours, remember everything. Yeah, sketch out the city from any viewpoint, but that's super rare. So this capability is superhuman. But there are other tasks which human is very good still. AI is not really good at. I think loose geometric modeling human is very good, but AI is not really good at yet. So suppose you are come to a park, see a nice monument object. Then maybe take a few photographs of the object and come back, given a laptop, make a 3D model content. And I guess I may not be able to do, but the 3D artist can likely do the task. Another extreme example I saw is from the YouTube on the internet. This is the opening movie of the animation, Jujutsu Kaisen. My kids love it, although I haven't watched it. So you can see the cool character jumping up from the building, flying down with the back downside and doing some like a magic. So our professional designer looked at the video and reproduced the scene with lots of effects. So this is a full 3D scene, 3D model dynamics, lots of things. But the artist can kind of get the sense of the scene from the animation. There's no 3D consistency. Some representation of a scene, then reproduce with precise geometry. So input are very loose, output are very precise. This is humans are very good at. We do that. But the AI is not really good at these days. So towards this really huge goal, I want to tackle the following problem. We're given a few pictures of an object without camera poses, because you cannot run SFM, just 2 images, so no poses. But somehow being able to render from any viewpoint, then maybe do some 3D reconstruction. Or you may be given 3 objects, 3 images instead. Again, no poses, but still being able to render from any viewpoint. And these 3 viewpoints can be arbitrary, maybe different every time. And you may have seen this. There are a whole bunch of papers doing reconstruction from a few images. So you think, oh, I have seen this, but probably most of them are in the following form, a bit different. You're given a few pictures with the camera poses, precise camera poses, then render from many viewpoints. You have seen a lot of these kinds. So when I see these works, I have to stop and ask a question. So wait, what do you mean by with the camera poses? Because as I said, you cannot run SFM. You have 2 images, go to park, but you can't get the camera pose. So this looks like a very strange assumption. So if you ask, how do you get camera poses? Usually you have a 3D model, digital model already, Google Scan Object Database, Objaverse. So you can render from any viewpoint, say pick 2, with a precise camera pose. That's why they have this data. But still looks like a weird to me. If you have a 3D model already, you have to use 3D model to make input for our system to recover a 3D model, but you don't have to do that. We have a 3D model already. So somehow a bit weird task, maybe except in the future, if you have a few view SFM in the future, maybe this makes sense, but I don't want to wait it. So this task is a bit weird to me. So instead, our task is given a few number of pictures of an object with without any camera pose. But we are still able to render from many viewpoints. Then maybe do some 3D reconstruction. So let's solve the task. So I call this a very loose geometric modeling. Loose in the sense of input condition. Output has to be precise, but input are very rough as we kind of do modeling. So I'm going to talk about the work done by my students, Stao, Jiachen, Fuyan, in collaboration with the Meta Reality Lab. So this loose geometric modeling is my terminology, although there are other very interesting papers who tackle this already. As far as we know, there are 2 really notable work. There are not many other kinds, I think. 2 works. First one from Google and SFU. My neighbor, Andrea, we live right across the street. The second one is from the UT Austin, my good friend, Qixing Huang. So these 2 works already tackle similar task. Then I want to compare how these 3 are different. So all these methods kind of solve the following task. I'm really skipping many details and it give you the higher level abstraction of these 3 tasks. So you're given input images, again, without camera poses. But again, you can run SLAM or SFM on these images, but somehow produce novel views of an object or scene. These are the tasks. So let's look at the first work, Scene Representation Transformer, or SRT, from Google SFU. So basically, given, say, 2 images, it can be 3 or 4, but say 2 images, just massage images with the CNN or Vision Transformer, anything. Get the latent image, massage features across images. So you get these. So standard stuff. Convenet something within image massaging, across image massaging. You get a latent image. Then using attention or cross attention to inject information into each ray of the target canvas. Then you can render. So this is the first paper. The second paper from UT Austin is very similar. So the difference is, so the first part is basically the same. UT Austin used Vision Transformer. SLT used CNN, but the same thing in short. The difference is going from this massage image feature into a voxel, a volume, as opposed to array. So previous one went to array by cross attention. This one goes to each voxel. So they produce a volume latent, volumetric latent codes, then do volume rendering. So rendering part is no learning, volume rendering. Previous one, decoding was actually some attention, but this is their approach. So some differences. So I think previous one, this one makes sense if you kind of follow the convenet transformer evolution. This really makes sense. If you follow more on NeRF and latent representation, this more makes sense. A volume rendering like NeRF style. So our approach is a bit different. We are more based on the multi-view diffusion model, a multi-view image generative model as a backbone, which we did in last year, MV diffusion, about using multiple stable diffusion model to make multiple images. Let me explain how we do. So we are taking both input images, say 2 input condition images, then 2 output target images. Everything, 4 images actually kind of the same. So you're kind of generating 4 views, both input, output, except input is input. So we have actual data. So we are using pre-trained image diffusion model, basically stable diffusion model, 4 branches to generate or denoise 4 images. And again, this is the input. So we have data. So this branch basically does not do anything. You have the answer is given. So don't do much. And this is a really noise. You have to keep on denoising. So if you're looking into self-supervised learning, you may realize this is really the masked training. You have the data, mask some portion, and infer. This is a form of multi-view diffusion model with masked training. Kind of if you follow self-supervised learning, multi-view diffusion model, kind of a standard actually framework. Then this is a multi-view diffusion model. So in addition to this architecture, this is the stable diffusion unit. You're going to have some cross-attention across the branches, kind of lightweight cross-attention branches here and here and here. So this is our architecture. So pretty much this is our architecture. We don't use any camera parameter anywhere. Input doesn't have any camera parameter, so there's no way of using it. Output views have a camera parameter, so we don't use it. They're all the same camera parameters, fixed it. So somehow network can learn what the first image is like, this camera viewpoint, but we never pass camera parameters. So attention is everything. Attention somehow figures out everything, solves it. Except you really have to have a massive amount of compute and data, maybe massive amount of compute to actually make things work, which may have helped us in getting the resource. So higher level, it's very interesting to me. So around this part of a network, the network kind of learns what kind of an object this is. They somehow reason the spatial relationship of these 2 images. So this is from like a top left. This is from the back top. Then some view 3D representation of the model somewhere here in the attention architecture, then injecting information to the target branches, again by attention. Then somehow being able to produce images here and there. So everything attention. We didn't have any special projection, nothing, just attention, regular stuff. So in short, these are to me the 3 notable architecture kinds, variants for this loose geometric modeling tasks. Again, top left is transformer combinate kind of a style approach, and top right is the NeRF style, NeRF plus latent volumetric code approach, and we are more in multi-view diffusion. So multi-branch image generative model way of approaching problem. So let's look at some results. Precisely our task is you're given a single or a few numbers of images without camera poses as input condition, then generate 32 images, actually 4 by 8, 4 along the latitude, longitude, and 8 along the latitude degrees. And this resolution, high res, fairly images. And given these, you can run any standard off-the-shelf NeRF. We use NUS, NUS system to get that 3D model. So these are already 3D consistent. So you can just run NeRF to get that 3D model. This is the first single image result. I guess you see this kind everywhere. Single image given 3D model. So actually not very surprising, just showing you. Here are the rendered nodal views, and then result of NUS, mesh reconstruction with some default texture mapping. Another example, yes, but kind of basic stuff. You shouldn't be surprised by this. You see everywhere. So what's surprising is, this is very surprising to me. So we have 4 input images at the top. Then bottom left is the reconstructed mesh model by using only the first condition as an input. This is the 1 and 2. This is 1, 2, 3, 4. So maybe first surprise is single view is very good already. Just given one image alone, you can get good 3D model. And it's difficult to actually spot where things are better, say in the right, bottom right. Because already, this is already very good. So if you carefully look, this is the one difference. So this, some details on the cabinet in the front side is only visible in the fourth view. So you don't see anything from the left too. But at the bottom right, you see something. So kind of network really knows that where this is. So somehow combine information from all the views. And this is also interesting. So first view alone, this is symmetric. So 3D modeling is very good, except the handle is a bit too thin because the side view here. So don't know the thickness. So second view gives you, oh I didn't realize. Side view gives you a thickness. So the handle, the head gets thicker, nice. And then 3 and 4 actually not really adding much. Symmetric, except when render from the, render from the bottom, you see the difference. So this bottom hole is only visible in the third view. You see the hole, maybe texture map or something, but the hole at the bottom. Oh, but maybe it's a texture mapping. Texture mapping, Texture mapping. So maybe this is not the real geometric detail, could be faking. But maybe this part, first view, second view, being able to merge information together for multiple views. So we did a bunch of quantitative evaluations. So this is the single view comparison. So because there are so many other single view reconstruction techniques. And although our focus is the multi-view without camera poses, but still really good, better than a lot. I think mainly because of the generative prior. Our network is based on the Stable Diffusion model, which are trained a lot massively. So they have power to make good the realistic models. So to me, that's one big difference. And next one is the sparse view without camera pose. Since there are not many other works, there are only 2 works who can do this before ours. And the latest one from UT Austin is a better one. So we compared against the leap from UT Austin on the image metrics at the right. And left, we use the mesh 3D metrics compared against the news nerve style reconstruction system by providing ground truth pose. So this is more like a standard reconstruction given camera pose. And we don't use any camera pose. So this should have an advantage actually. Although surprisingly, so if you look at these top 3, our results are actually much better than the news with the ground truth pose given. And the observation is suppose we use news with the 4 views. News basically takes 4 views with a camera pose and doing reconstruction. We use news at the end, but we take 4 views, then generate 32 more views by using our system, generative prior. Then run news on 36 images instead of 4. And that really pushes the performance. If you're given 10 images, that's already enough for like a multi-view. The news does actually fairly well. So we don't have much like advantage. Actually, we are worse slightly, but for very sparse view cases, we're adding lots of information about the generative prior. That's the, I think, interesting. So if you want to see more results, single view results or multi-view results, there's a link to here or MV Diffusion++. You can find many more examples. So that's the first, very loose geometric modeling. So now I want to talk about the very complex CAD models. I guess Richard already gave you a good message. We should do more CAD modeling. So I don't really have to explain why CAD is important. So CAD is good for designing, running some simulations, or maybe just manufacturing stuff, very key. Or to fly to Seattle, you need this. You have to have a CAD to make these like complicated mechanical parts. And also BREP, I don't have to explain, Richard already gave a presentation. The BREP is the standard representation. So our work generates the BREP model. Actually something complicated. These are the raw results our system is generating. But then there's some post-processing to get this the BREP model. Watertight, nice parametric surfaces and the edges in between. And I call this very complex CAD models because it's complex, what I call structured geometry, consisting of not so complex hierarchical elements, meaning faces and edges and vertices are not actually very complicated, nice and smooth. Edges is usually a line or cursive line, not very complicated, but their combinations and relationships are very complicated. So I call these very complex. Of course, I am a researcher, so I think this is very complicated. If you are more on the modular artists, they are far from being complicated. You may laugh at us, but I think the BREP generation, this is maybe the limit right now. So they're not really complicated, but I think as a researcher, I think it's very exciting. Very complex CAD model. It's difficult to generate by the current system. So this work is done by my student, Sam Eric, in collaboration with Autodesk. I will be in Denver, SIGGRAPH, next month. For CAD modeling, there has been some trend on treating CAD model as a language, a sequence of tokens. And this is the seminal work from Columbia, DeepCAD. In short, CAD model you make by a sequence of geometry editing operations. So CAD model is a sequence of some commands, like adding edge or lines or do some operation. So this model you can write down as a language. So actually this is first word, second word, third, and so forth to the bottom. And by defining the language at the right. So this is like grammar of geometry editing operations, and any CAD model is a sequence of these like words. And if you know that your model is a language, how do you generate? Just ask ChatGPT, auto-regressive transformer. So if everything is a language, generate yes, whatever successful from NLP. And that's basically the story. So our prior work on ICML for the past 2 years are basically that, the language. So kind of borrowing techniques from NLP to generate. That's how we did it. And gives you kind of a nice model. This is the generating a sequence of commands to make these CAD models automatically. The issue is that usually we don't keep track of the sequential data. So once we make a model and publish the model, you throw away those sequence operations, just final model. BREP model will be published, shared, but actual editing history will be thrown away. So as a data set, you don't have much bigger database of this sequence CAD representation. On the other hand, BREP is the standard. There are a lot more. So with the emergence of really scalable, powerful architecture like a transformer, which can use a lot of data, it's better to handle BREP as opposed to sketch and extrude, simply the amount of data you may find on the internet. So now back to, we focus on generating the BREP model instead of sequence, because of the abundance of data out there. So what is a BREP model? It shows you these images at the end of the animation. Let's take this toy example. So BREP model is a solid object bounded by a set of interconnected faces, edges, and vertices. Sounds fancy, but very simple. So here, this colorful stuff, 4 things, actually, there are 2 hidden, 2 or some hidden behind. These are faces. And each face is surrounded by a sequence of edges. And so these ones are the edges, of course. And each edge starts and ends at a vertex. And also edge meets another edge at a vertex. So kind of makes sense. Vertices, edges, and faces. Then when you talk about generating BREP, you have to generate the following quantity. First of all, geometric information of face, edge, and vertex, meaning the coordinates, where the vertices are, what are the shapes of the faces, or are the shapes of the edge. So edges can be a curvy, not like a line segment. So you want to represent somehow edge. And also the topology. Say this edge is shared by these 2 faces. These 3 edges meet at this vertex. This kind of relationship must be also somehow represented or generated. But it's actually difficult to generate. So if you look at the successful Gen AI systems, say image, so you kind of a diffusion model. So take a noisy image H by W pixels, then spitting out cleaner denoise H by W. The video generation, you take H by W by F pixels, and then denoise to spit out H by W by F. And if you are somehow maybe graph, you're given a graph and generating the properties in a graph. Thanks to transformer, you can see the transformer diffusion model, denoise. Or NLP is next token prediction, so kind of given n predicting the next one. So all these actually, before starting denoising, you actually know how many variable things to generate a denoise. So maybe I call this fixed known dimensional structure. I know exactly these are the set of things have to generate. I know already. That's not the case for actually BREP. So let's look at what the quantities are difficult for the looking at the existing successful examples. Vertex may not be bad. The vertex XYZ coordinate, so 3D. So I know the exact dimension of the vertex. Edge can be again curved, but let's say I do some interpolation. I represent every edge by 10 vertices. So I need 3 by 10, 30 values. So again, it's a fixed dimensional. I have to generate 3 by 10 values per vertex, per edge. Face is a bit tricky. It's kind of a special shape, so not sure how to represent face by some fixed dimensional structure. I have to scratch my head, and topology is the hardest one. Again, before generating a model, I don't know how many faces or how many edges, how many vertices have to generate. So I don't know what are the variables to generate, so I cannot apply the model, say diffusion model, easily. So our approach idea was we want to find an equivalent representation, equivalent fixed known dimensional structure. So I want to somehow find the equivalent representation whose dimension is fixed, equivalent to the BREP model, whose numbers of faces and vertices may vary, for example. So as I said, vertex is easy, XYZ, edge is easy. So I talk about how to actually represent face and topology as a fixed dimensional structure. Then I can apply existing, say, DM, diffusion model, easily. So let's take this face. So in the BREP model, you also have the UV axis attached. So looking at this, this is a UV plane, and this is the face. I'm going to just represent as a 6 by 6 sampled points on the surface of the face. So 36 points 2D coordinates. So 6 by 6 by 3 is a representation for each face. So another face again, same, 6 by 6 by 3. So any face I represent by the fixed dimensional data structure. Then if I want to really get the parametric smooth one, I can just maybe do surface fitting later to 6 by 6 by 6, 6 by 6 by 3 structure. And for the topology one, so what we have basically is each face, its geometry is represented by 6 by 6 by 3 3D tensor. And the edge, let's say again, use 4 points to represent along the edge. So maybe 3 by 4, 12-dimensional vector. And the vertex is XID, 3-dimensional vector. And connections are basically the relationship. So say this edge is shared by orange and green face. So these two feature vectors, tensors are connected. And this vertex is incident to this edge, and that edge, although I'm not writing this. So these things are connected. So you can basically representing edge, vertex, face as a node. The connections represent the topology information. So I basically have to generate these geometric parameters, also connections, which two are connected. And then we have a full representation. But again, we don't know how many faces and how many edges. So the size of the structure vary per sample. I may have to have 10 faces and 6 vertices for this BREP model, but 12 and 13 for the other. So dimension change, which is bad. So here's how we make the fixed dimensional BREP representation from here. So first order top is just a root node, fake node. Put the face node next level, edge node next level, then vertex node at the bottom level. So this is the same equivalent structure. So first, I'm going to duplicate the shared geometry. So this yellow thing is shared by 2 faces. Blue vertex is shared by 2 edges. And I don't like this looping structure. I want to make everything edge. So first, duplicate the shared structure to make everything a tree. So again, here, this yellow thing is shared by 2. I duplicate, and then like a separate. Same thing for the blue. It was shared before, but separate. Now everything is a tree. But this is still not fixed dimensional structure because this face has 1 child. This face has 3 children. It's different, it's bad. So I want every face to have the same number of children. So we are going to do padding. So I have to do the typical trick, not beautiful. But say in this example, every Burette model has at most 2 faces. And every face has at most 3 edges. And every edge has like 2 nodes, actually, start and end. In reality, these 2 and 3 are much higher number. But in this example, there's 2, 3, and 2. So given this, I'm just going to pad. So every face must have 3. So I can randomly pick 1 and then duplicate. Then I make sure that these are 3 children. And then for every single edge, I have to have 2 vertices. So kind of duplicate. So by duplication, I can make sure that every Burette model has 2 faces, and every face has 3 edges, and every edge has 2 nodes. And I can just make sure. Now any Burette has the same dimensional tree structure. Hope this makes sense. So now given this, so we are basically using Burette model to generate the geometric parameters 6 by 6 by 3 or 3 by 10 or 3D vector for each node, where the tree structure is like a static, fixed. Then this actually geometric parameters actually give us back the topology information as follows. So suppose I generate all these geometric parameters. I can first do undo padding. So these say 3D coordinate along edge happens to be very similar after generate. So I kind of know that this must be the result of padding. So I can just say, oh, this must be the same thing. So I'm going to merge it. This is again heuristic. I have to have a threshold, very sensitive threshold. But another here, oops, sorry. Again, these somehow edge are very similar. So must be padded. So I'm going to merge it. Then now after undo the padding, I also have to undo the duplication. So these 2 looks very similar in terms of the eigenedge. And these 2 are very similar in terms of the coordinates. So I identify those edges which are similar with some thresholding. Then I can merge it. But then I also, oh, these are similar, I merge it. So after generating the geometric parameters with a very sensitive, this nasty part, thresholding, we keep merging to recover the topology. So that's how we do. Yeah. Then after we do that, we can recover the full structure. So that's how we do. And to be precise, we know that now our Burette is always the tree structure with the same numbers of nodes. And we do diffusion model actually by level. We first generate the faces. And then after that, given that generate diffusion model, generate or denoise the same number of the edges. Then after that, generate the same number of the vertices. Then undo padding, undo the duplication, then get the tree structure. So let's look at the results. The top left, you see the faces. The faces are without the boundary, so you kind of see the faces extend. And then this is edges and vertices. Then after some or very complicated post-processing, we can get this watertight model. Basically, for each face, I have to use a boundary to clip it and then connect things up. A bit tedious, but yes, we can do. And more examples. And we can also do the conditional generation. So say, look at the row by row. So look at this row, you are given this. So your result model must have this part somehow, generate. Then changing noise and make 3 examples, we get these 3 models. So this part is like a common thing. And very easy to do because we do the masked training anyway. So given a tree, we specify values for like a certain nodes. Then for the remaining one, we just infer. So this is the basic mask training, part of mask training. Or these 2 are given. So you have to have this and that. Then still generate different kinds. So pretty kind of interesting, the conditional, easy to apply. And for more, lots of evaluation, it's a SIGGRAPH, so lots of evaluation we did it. You can refer to the paper. And you can just make many models. So to summarize, the BREP model is very complex with the research standard, very complex structured geometry. Our approach is to find equivalent fixed dimensional structure where the current Gen AI technology, basic diffusion model for the vision, is very successful, and you can apply. So that's our second work, and the first work is about the some approach to solve loose geometric modeling, or maybe I call generative reconstruction. And I think the interesting research ahead is the second one, the BREP model. We basically avoid the real task. The really cool thing is to somehow generate this arbitrary topology, the varying degrees of freedom of structure straight, as opposed to finding this equivalent fixed dimensional structure. So to me, that's very interesting if you can directly infer more topologically varying structure along the way. Easy way is to kind of doing auto-regressive wrapper around diffusion model and keep on evolving, but that's kind of dirty. But I don't have idea how to do that well. And second one is in terms of just a field. I think loose modeling is very interesting, but very few people work on. But this is really the human perception. I look at the model, a chair model. I don't have a precise depth measurement, unlike depth camera. I don't know exact dimension, but I can still make a model in my mind, produce some model with precise geometric details and effects, which the current AI system is not really able to do. So I want to see more and more this loose geometric, or what I call conditional generation, or generative reconstruction work from our field. So that's all, and thank you very much for your attendance, and happy to take any questions.
Questions, please come to the stage here.
Thank you, Professor, for the great talk. I really enjoy your BREP gen a lot. And what do you think is the limitation of the BREP gen currently?
Yeah, thank you for the great question. So the biggest limitation is after we generate those faces and edges and vertices, we have to make the final model. So there's a big jump actually from the top, these two, to the bottom one, the actual BREP. So basically, we have to make sure that the face we generate here and other face must match exactly. So actually 50 to 60% of the time we actually succeed in the conversion. And 40% of the time we actually fail, invalid. So failure rate is very actually high, which is a problem. Could it be okay as a generative system? If things fail half of the time, just run twice as more. So if you can wait twice as long, yes, why not? But we may be missing certain modality if you just drop. So that's the biggest issue. So yes, I think, yeah, that's the biggest issue. We basically fail. And we have some idea how to make sure that this post-processing never fail actually. So we have a procedure to actually, after generating this kind of a thing, this conversion is always going to work 100%. We are in preparation. But again, actually similar, finding equivalent special representation, which is equal to the BREP. And post-processing from the equivalent representation to the BREP is never fail, it's going to fail, special one. But still equivalent representation. I want to directly infer varying topology. That's a real hard problem. I want to see some solution. Yeah.
Do you think, so when we consider BREP, there's the ABC data set, but compared to meshes or images, there aren't a lot of data sets, right? What do you think then is are there any limitations in the data set?
Oh, yeah, I think so. There are many limitations. This really just CAD model is harder to make. Human has to make. Images and point cloud, I guess meshes are kind of easy because we can scan. So when people talk about self-supervised learning, excuse me, often people say that, oh, there are lots of data. So we can do self-supervised learning, not really for the CAD. With CAD, the data are the human creation, which is scarce. So we can really exploit the, I guess, cell by learning much. So I don't know. Typical ways to have some differentiable renderer. A CAD model rasterized to some images. Then loss come from images, but somehow not very powerful. So I think lack of data is really hard, a difficult problem. And I don't see a good solution. Maybe if you're a big company, access to client data, you have it, but researcher is very difficult.
You also for a great talk. So I have a question about BF. I'm not that familiar with BF in general, but it seems that you learn the connectivity and the geometry.
Yeah.
So the geometry comes from the vertices, and I think the edges, right?
Also faces, yes. Faces as the 6x6x3 3D coordinates. Yeah.
In your representation,
Yes.
but in BREP, do we need really to know how the faces are?
Yes.
Like, or if we have edges and vertices, is actually enough to reconstruct?
Let's see. So I guess you kind of know that the not equivalent, meaning it's possible that given the edges, how to fill in the face in the middle can be different, how much curvature. So yes, if you don't represent faces, you lose some information from edge and the vertex only, like a pure, like, I don't know, high curvatures or like much flat. That's information not stored in the edges and vertices.
I see. And in BREP is controlled by a parametric representation,
Usually it's parametric, yes. Usually parametric, which we do not want to. We can regress somehow B-spline surface parameters, but somehow we are scared. So we use the 6x6x3. Then we can do that.
If they actually learn the parametric representation.
Oh no, more like a 3D coordinate grid. 6x6x3.
I know what you're doing,
Yeah.
but I'm saying that in BREP representation, if we actually in your representation, if we actually learn the parametric values. Like
I know, just a 3D coordinates. So we convert parametric to the coordinate.
Possible or not?
Possible, I see. It's basically, do you go for the algebraic representation parameters?
You can just learn the B-spline. If it's a B-spline, you just need to know the control points. The control points are basically the edges.
Yes.
And then you know the degree, and then you're done.
Yeah.
But here you're making a lot of points, and that's your point cloud. And then you're learning it based on point clouds.
Yes.
So probably I'm saying that if you use if you learn the connectivity using the approach that you're doing, and then make the parameters, the number of parameters that you learn, a lot lower instead of point clouds.
I feel pretty feasible. Yes, control points, just kind of sparse points instead of dense. So even somehow latent code, as opposed to, so instead of like control point, somehow latent code generate, then that decoded back to control point or something. It seems actually pretty feasible. We have so many other stuff going on for the work, so we didn't touch it. Something very primitive for the face representation, but yes, it seems pretty feasible.
Thank you.
Hi, Professor. I also have a question for reaction. I know that you proposed a new furniture dataset, right?
Yes, yeah.
And it only contains like 6,000 BREF. I mean, is 6,000 really enough for generating new shapes?
Good question. Let's see, I think we haven't explored much how much more extrapolate or generate new kinds. So maybe, honestly, I don't know. Maybe less likely so. Maybe some tendency of generative model community. Just take the model and then produce. And that distribution is similar to the training set, and we are happy, as opposed to extrapolating much. So we haven't done that type of actually evaluation much. We could do something similar for the other floor plan. So for example, somehow, I don't know, what's the way? Keeping certain chair categories, I don't know, European chair, Asian chair, then somehow trying to generate other kind African chairs, actually, I don't know. But we haven't done. We lack of data. We want to use lots of data for training. Yes, we couldn't do.
Due to time limit, so if you have questions, please chat with Jasper afterwards. So let's thank the speaker again. So, well, it's I think
Thank you again for the presentation, and thanks to all of our